to help them improve their research and hopefully publish it as long papers or journal articles in RecSys or other venues. So this is going to be the 5th FAccTRec workshop, and which is going to be hybrid for hopefully next year it's going to be in person again. Maybe also it's not a bad idea to also have these workshop as hybrid. I myself, I was an international student, so I benefited a lot from these online and virtual conferences and workshops. So this is still beneficial for us. So this year, like similar to the previous years, we're focusing on responsibility, fairness, accountability, transparency, compliance, and safety. So these are the main topics that we are focusing on, and the papers, the authors that submitted their papers have been mainly focusing on this, but we're accepting any other topics related to this, which we're going to see throughout the workshop. So we accepted position and research papers. Position papers are offering a lot of new ideas and proposed directions for the research, and also they're adding up new ideas to the topics that we are exploring in this workshop. And research papers are going to discuss their empirical and analytical results, which we're going to see in a little bit. So this year we had 25 submissions, which is more than last year, which was 14. And 13 research papers, 12 position papers, and we accepted 10 long papers and 9 short papers, which the research papers, 6 of them are long papers and 2 of them are short, and the position papers, we have 4 long position papers and 7 short position papers. And every paper had at least 1 or 2 reviewer. And you can access all the articles from our website. And if you go to the program tab, you can access most of the papers. And this is the QR code for our website. You can scan it and see if you need more information on the papers. So we're going to have 6 sessions, which 4 of them are online, including this. Our speaker is also going to be presenting online. And each long paper has 17 minutes to present and 3 minutes for Q&A. Short papers have 8 minutes to present and 6 minutes for discussion. We are going to discuss the questions both in chat and live. So please use the microphone to ask your questions. So we will be fair and discuss the questions that are asked online. So the workshop will be recorded fully, and the question part will be removed after we take the recording. So we're going to have a lunch break from 12:30 to 2 p.m. and the workshop will end around 5:30 p.m. So this year, our speaker is Liu Zhang. He's an assistant professor from the Computer Science and Computer Engineering Department from the University of Arkansas. And the presentation will be on causality-based fair machine learning for sequential decision-making.
Yeah, thank you very much for the introduction, not introduction. So, okay, my name is Lu Zhang. I'm an assistant professor from the University of Arkansas. And it's my honor to be here to talk about my research. The title of this talk will be the Causality-based fair machine learning for sequential decision-making. Okay, so I believe that the audience of this workshop should be familiar with the topic fair machine learning. So the goal of the fair machine learning is to learn the machine learning models to make decisions such that those decisions are not biased or discriminatory against a certain group of people. We have a more formal definition of the discrimination, which refers to unjustified distinctions of individuals based on their membership in a certain group. And as we know that discrimination is prohibited by laws and regulations in many countries in the world on several grounds such as gender, age, marital status, race, religion or belief, disability or illness, and so on and so forth. These attributes are referred to as protected attributes. The reason why the machine learning may induce bias or discrimination in the decision making is because, first, the data that is used to train the model may contain bias because those data are collected from the history. So they may contain the historical bias. When we use this training data to train the model may also inherit the bias and sometimes may also amplify the bias contained in the data. And another reason here is that the traditional machine learning algorithms may also introduce new bias. So as a result, the predictive model may contain bias, and when we deploy them to make the decisions may be biased. And as I said earlier, the goal of fair machine learning is to build discrimination-free predictive decision model. Currently, the most studies in fair machine learning are based on static settings where one-shot decisions are made on tasks such as classification and regression. However, in practical situations, the decision-making is more of a sequential nature. So here we can have different aspects to understand and to describe the sequential nature. We may have different sequential settings. In this talk, I will mainly focus on two sequential decision-making settings. In the first setting, the decision models are deployed and make decisions sequentially. And in the second setting, the data arrive and are observed sequentially. So we can see that both of the situations here are sequential settings, and we will talk about how the fair machine learning can be made under these two situations. Fair machine learning is in the sequential setting is still underexplored. So in this talk, I will mainly introduce three works. In the first work, we study multiple decision models which are connected in a partial order. And in the second work, we want to study the situation where there is a single decision model that is executed repeatedly and creates the feedback loops. And in the third work, we will study the online recommendation setting where customers arrive in a sequential manner. Before we move on to the three works, let me first talk about some background and the preliminaries. So we will talk about the background of the structural model, causal model, because we will make use of the structural model, causal model to define and quantify fairness. So the structural causal model is a causal inference framework developed by Yuda Perl in 1995. It is a mathematical framework for describing the causal mechanisms of the system and the set of structural equations. The structural causal model can describe how causal relationships and causal effects can be inferred from the observational data, and sometimes plus some domain knowledge or domain assumptions. Symbolically, A structural causal model is a triple that consists of three components, U, F, U, V, and F, where U is a set of exogenous variables whose values are determined by factors outside the model. Sometimes we can simply refer to the exogenous variables as hidden variables. V is a set of endogenous variables, or sometimes we simply call them the observed variables, whose values are determined by factors within the model. And finally, F is a set of deterministic functions where each function is a mapping from the Cartesian product of the U and V to each element or to each variable in V. And here we usually call the independent variable in V the parent of the dependent variable xi. Since the structural causal model is a mathematical model, so to simplify the understanding, we can illustrate a causal model by a graph called the causal graph. A causal graph is a directed graph where each node in the graph represents a variable in the causal model, and each edge represents the mapping structure that is defined by the structural equations in the causal model. Or to be more specific, each direct edge in the causal graph represents the direct causal relationship or potential direct causal relationship. Due to a cyclicity of causality, the causal graph is usually a direct causal graph, is usually a direct acyclic graph or DAG. Here's an example of the causal model and the causal graph. So suppose that we have 4 observed variables, and we also have 4 hidden variables, where each hidden variable is corresponding to one observed variable. And a toy causal model can be given like this, and its associated causal graph is given like this. So here we may note that some observed variables may be confounded by some hidden variable. So in that case, we can use a double-headed dashed arrow to connect the hidden variables that are corresponding to those 2 observed variables, for example, I and H in this case. We can also assume that there's no hidden confounder. If we make this assumption, then the causal model is called the Markovian model. And in that case, in the causal graph, we can simply omit all the hidden variables. And then by giving the causal graph or the causal model, we can infer the causal effect, which is facilitated by an operation called the intervention, or to be more specific, the Hart intervention. The Hart intervention is the basic operation of manipulating a causal model. It simulates the manipulation of the physical mechanisms by some physical interventions or hypothetical assumptions. The meaning of the Hart intervention is to force some observed variables to take certain constants. Mathematically, the intervention is formulated as a do operator. And since the variables in the causal model are causally connected, so when we perform the intervention on one variable, then that intervention will affect some other variables in the causal graph, which are descendants of that variable. The effect of the intervention on other variables can be represented by the post-intervention distribution. In addition to the Hart intervention, we also have the soft intervention. The meaning of the soft intervention is to force variables to take a functional relationship in responding to some other variables. For example, if we want to force the variable y to take a functional relationship in responding to x, where the function is given by a parameterized equation h theta, And then we can perform a soft intervention like this. The effect of the soft intervention can also be represented by post-intervention distributions. When certain assumptions are made, for example, the Markovian assumption, then both hard and soft interventions can be computed from the observational data by using techniques such as do calculus or sigma calculus. So we will skip the detailed causal inference techniques in this talk. And then by utilizing the intervention, which can be either a hard intervention or soft intervention, we can compute the causal effect. There are different types of causal effects. The first type of causal effect is the total causal effect, or simply the causal effect, the total effect. The total effect measures the causal effect that is transmitted along all causal paths from the source variable to the target variable. Usually, we represent the causal effect as the difference between two post-intervention distributions under two different interventions. For example, here, the total effect of x on y under two different interventions, do xy and do x2, can be given by this difference. Here's another example, supposing that we want to compute the total effect from the variable h on the variable e. So in that case, we can perform the hard interventions on the variable h and compute the difference between the two post-intervention distributions. When we perform the intervention on h, note that this intervention is transmitted along both passes from h to e, which are highlighted by the red arrows in this causal graph. The next type of causal effect is called the path-specific effect, which measures the causal effect transmitted along certain passes only. Given a subset of causal passes, pi, the path-specific effect from x to y under two interventions, do xy and do x2, is given by this difference. Here, we usually call the value x1 as a reference value because the meaning of the path-specific effect is that suppose that we first perform the intervention to fix the value of x to x1, where this intervention is transmitted along all causal paths. And then after that, we perform another intervention that changes the value of x1 to x2, but this time, this intervention is transmitted only along causal paths in pi. So by using the same example here, supposing we use h equal to 1 as the reference value. And then we will perform the second intervention that changes the value of h to 2. The effect of this intervention only passes through the indirect path from h to e, which is highlighted by these red arrows. And the last type of causal effect we will introduce here is called the counterfactual effect. The counterfactual effect measures the causal effect while we have certain observations or evidence. For example, the causal effect of x on y under two interventions, x, y, x2, given that we observe O is equal to O, it's given by this difference. So here, the variable set O can be any subset of the variables or features we have in the data. So for example, suppose that we want to compute the counterfactual effect of H on E, where we have the observed values of H, which is equal to 1, and the observed value of E, which is equal to B. And we want to compute, we want to know what if we perform an intervention on H, which changes the value of H from 1 to 2. We want to know what would the probability of E equals to AB. Okay, so to compute this counterfactual effect, we can consider the causal graph, which is showing here, which consists of two worlds. The first half of the figure shows the counterfactual world, and the second half of the figure shows the factual world. In the factual world, we have the observations on H and E, so we condition on these two variables. And in the counterfactual world, we perform the intervention on H, and we want to measure the effect of H on E, which are passes through this two causal passes. And meanwhile, you may note that these two words are connected by the double-headed dashed arrows because those two words share the same exogenous variables. By applying those causal effects to the fair machine learning area, we can define the causality-based fairness notions. Supposing that we use S to denote the protect attributes, where we assume the protect attribute is the binary attribute, so that we use X plus to represent the advantage group, such as male, and S minus to denote the disadvantage group, such as female. We use X to denote other profile attributes, and we use Y to denote the decision. Then the demographic parity can be formulated as the total effect of S on Y is equal to 0. The direct and the indirect non-discrimination can be formulated as the positive specific effect of S on Y is equal to 0, where the path set pi varies for the direct and indirect non-discrimination. So for the direct discrimination, we use one set of paths as the pi, and for indirect discrimination, we can use another set of passes as pi. And finally, counterfactual fairness is formulated as the counterfactual effect of S on Y given the observations on X is equal to 0. Okay, so given the background, now we are ready to talk about the research works. The first work is about fair multiple decision making. In this work, we consider a problem where there are multiple decision making tasks, such that there are those decision making tasks or models are interconnected, such as one decision model may influence another downstream decision model, and the feature distribution may also change due to the deployment of the decision models. We may assume that all decision models may contain discrimination, which can either be introduced by themselves or transmitted from upstream models. And the objective here is to build fair machine learning models for all decision-making tasks. Solving this problem is challenging because simply building a fair machine learning model for each task independently may not work. Let me use a very simple toy example to explain this. Suppose that there are two decision-making tasks. In the first decision-making task, we use X1 to predict Y1, and in the second decision-making task, we use X2 to predict Y2. In addition, the decisions of Y1 can also influence the distribution of X2. And the target here is to build fair decision-making models for both Y1 and Y2. So let's first look at how the traditional method may solve this problem, where we want to build the two decision models separately. The first step of doing so may be to collect the data for both decision tasks. So suppose that we have collected data for X1, Y1, and X2, Y2. And then based on the collected data, we can build the classifiers for two tasks separately. And here we can leverage the state-of-the-art fair machine learning techniques to build fair classifiers. So we may assume that both H1 and H2 are fair in training. However, when we deploy the two models for making decisions, the decisions made by H1 can still be fair, but the decisions made by H2 may not be fair anymore. This is because the distribution of X2 is influenced by the decision Y1, and the decision Y1 made by H1 may not be the same as the decisions in the data because of the fairness constraints that we impose when we train the model H1. So as a result, the distribution X2 will also be different from the original distribution of X2 in the data. And since H2 is trained on the original data distribution on the data, it may not be fair anymore on the new distribution of X2. To solve this problem, we propose to leverage the structural causal model, treat each decision model as a soft intervention, and infer the post-intervention distributions to formulate the loss function as well as the fairness constraints. The advantages of doing that, are that first, we can learn multiple fair classifiers simultaneously by only using the static training data. The second, after we infer the post-intervention distributions, we can easily employ the off-the-shelf classification models and optimization algorithms for solving the problem. And finally, since the framework is built based on the structural causal model, it is straightforward to achieve causality-based fairness notions. In this work, we still use total effect as a fairness notion for simplicity, but the framework can be easily extended to other causality-based fairness notions. Let me use a simple example to explain how this idea works. So suppose that we also have two decision-making tasks, X1, Y1, and X2, Y2. And we also include the protected attribute S here in this causal graph. And the causal connection among the attributes are more complex than the previous example. So in this example, we may first build a classifier for predicting Y1. And suppose that this classifier is denoted by H1. And then for any H1, we can perform a soft intervention to simulate the deployment of this classifier. And then the distribution of X2 after the deployment of H1 can be inferred as the post-intervention distribution of X2. And then when we build the classifier H2, the input data X2 will follow the post-intervention distribution instead of the old distribution in the data. And then we can formulate the loss function as well as the fairness constraints based on the soft intervention, based on the post-intervention distributions of the soft interventions. So by using this way, we can simulate the distribution after the model deployment. One thing to note here is that in this process, it seems that we are performing the soft intervention one by one in a temporary order, where we perform the soft intervention H1 first and then followed by H2. However, in causal inference, when we perform multiple interventions, those multiple interventions are performed at the same time, and the post-intervention distribution are inferred, assuming that both soft interventions are performed. So we don't need to perform the two soft interventions one by one, but instead we can perform them simultaneously. In general, we may have L decisions, and for each decision, we want to build a fair classifier. And then the soft intervention is just to deploy all the decision models. Based on the post-intervention distributions, we can formulate the loss function and the fairness constraints. Traditionally, the classification error of a classifier is formulated as the empirical risk. We also formulate the classification error as the empirical risk, but the difference here is that the attribute follows the post-intervention distribution instead of the observational distribution in the data. The fairness constraint is also formulated similarly based on the post-intervention distribution. And then by using the causal inference techniques, including the dual calculus and sigma calculus, we can infer the formula for computing the loss function, the post-intervention distribution from the observational data we have. So this is a formula derived, and note that here we have a function phi, which is a surrogate function to ensure that the loss function is differentiable. And similarly, we can infer the formulas for computing the fairness constraints from the observational data. And then it is straightforward to formulate a constraint optimization problem where the objective is to minimize the risk, empirical risk of all classifiers, while the constraint is to ensure that each classifier is fair. For solving this problem, we can adopt the Lagrange multiplier technique to add the constraint into the objective function as a regularization term. And the problem can also be easily solved by using gradient-based algorithms because each classifier is involved at a single term in the multiplication, so that we can easily compute the partial gradient with respect to the parameters of each classifier. We also analyze the excess RecSys bound to ensure that the optimization will converge. In the experiments, we use both synthetic data and adult data. The adult data is real-world census data that consists of tens of attributes and thousands of individuals. We've built a causal graph by using PC algorithm over this data, and then we treat age and the protected attribute. We treat work class and income as two decision tasks. For the baselines, we consider three baselines. The first baseline is an unconstrained method that does not consider fairness at all. Then we consider a separate method where each classifier is learned separately on the training data to be fair. Then the next baseline is called the serial method, where fair classifiers are learned sequentially following the topological order of the causal graph. And finally, the joint method formulates the joint method formulates the optimization problem on the training data to learn all classifiers simultaneously. In the experimental results, we can see that for our method, we can achieve fairness in both training and testing phase while achieving good accuracy. But for the separate method, although it can achieve fairness in training, it cannot achieve fairness in testing because the model deployment changes the data distribution, the feature distribution. Okay, so now let's move to the second work, which is about the fair repeated decision making with long-term impacts. This problem is related but different from the previous problem. In this problem, we consider that there is a single predictive model that is executed repeatedly and makes sequential decisions over a period of time. This problem setting is actually very common in practice. So think about the loan application example. Suppose that the bank has the decision model for making the decisions based on the attributes of the applicants. And each applicant may apply for the loan multiple times. So those multiple applications form a sequential decision-making process where the bank will use the same decision model to make multiple decisions repeatedly. And in this process, similar to the previous problem, the decisions made by the decision model can also influence the feature distributions. And in this context, it is more clear that this influence will form a feedback loop between the decisions and the user features. For example, in the backloading case, the back may use the applicant's credit score to make loan decisions. And on the other hand, the back decisions will also affect the applicant's credit scores. So that's how the feedback loop is formed. And for this situation, several researchers in fair machine learning field proposed that fair decision making should concern not only the fairness of a single decision, but more importantly, whether a decision model can impose fair long-term effects on different groups. This notion of fairness is referred to as long-term fairness. To achieve long-term fairness, there are additional challenges compared with the previous problem. One challenge here is how to define notions and quantitative measures for long-term fairness. And another challenge is how to develop efficient algorithms for dealing with the repeated feedback loops in the dynamic system. In this work, we propose to utilize the structural causal model as well to address those challenges. We assume a causal graph for describing the causal relationship among variables over time. So here, since the time is involved, the causal graph is called a time-lagged causal graph, where we use separate nodes to represent the same variables but at different time steps. So for example here, suppose that we use X to represent the user feature and Y to represent the decision. And then we use X1 and Y1 to denote the features and decision and the first time step, use X2 and Y to denote the feature and the decisions at the second time step, and so on and so forth. And the objective here is to achieve fairness at a certain time step denoted by T star. We also consider to use the software intervention to simulate the model deployment. Different from the previous work, in this problem setting, we assume that there is a single decision model, H theta, that is deployed at every time step. Then we formulate the long-term fairness as the path-specific effects that are transmitted in the time-lag causal graph along certain causal paths. We divide the features into two groups. The first group is the irrelevant features or irrelevant attributes. Those are attributes that are justifiable in decision making, which means that those attributes may evolve autonomously, or they may be altered by some external factors. So the decision makers should not be responsible for any bias or discriminations that are caused by those irrelevant attributes. And then the remaining attributes are called relevant attributes. So the long-term fairness is defined as the path-specific effect from S to Y T star, where the causal passes through relevant attributes only. For example, in this causal graph, if we treat all attributes as relevant attributes, then the long-term effect is formulated as a path-specific effect that are transmitted along those red paths in the causal graph. In addition to the long-term fairness, we may have two other requirements. The first requirement is short-term fairness or local fairness, which may be stipulated by laws or regulations. We define the shorter fairness as the direct discrimination from the protected attribute to each of the decision model. So for example, in this graph, the short-term fairness is represented by the causal effect passes through those green arrows. And the other requirement is the utility, institution utility, which can be simply measured by the aggregate loss over all time steps. So one thing to note that in all of the above definitions, we use soft intervention for modeling the decision model deployment, and the loss function and all the three quantities are formulated based on the post-intervention distributions after performing the soft intervention. Then we can formulate the problem as a constraint optimization problem, where the objective is to maximize the utility while subject to both long-term and short-term fairness constraints. Solving this optimization problem is more challenging than the previous problem in the previous work because first, we have a potentially long sequence in the decision-making process. And the second, since we adopted the single decision model at every time step, so this means that this classifier is involved in multiple terms in the multiplication, which makes more challenging to compute the partial derivative. So to efficiently solve this problem, we propose to convert the problem into reformulate the problem as the performative risk optimization problem. And then we propose to adopt the technique called the repeated risk minimization to optimize the problem. We skip the technical details here. And then for experiments, we consider the unconstrained logistic regression model, the logistic regression model with demographic parity, as well as the logistic regression model with the equal opportunity as the constraint. For the data, we use both synthetic data and the semi-synthetic data. For the synthetic data, we simulate a process of backloadings following the above causal graph, where the dynamics between two consecutive time steps is given by those formulas here. And then for the semi-synthetic data, we use the Taiwan credit card data set as the initial data in our simulation. Then we run the simulation for 5 times and train the models on the sequential data. And for the results, we can see that for the baselines, the long-term fairness kind of accumulate over time, which becomes larger and larger with time. And on the other hand, for our method, we can reduce the long-term fairness gradually with time. We also analyze the convergence of the repeated risk minimization technique in our problem. The experiments on the semi-synthetic data show similar results. Okay, so the last work will be the fair recommendation in online stochastic setting. In this work, we consider a contextual bounded recommendation setting where the data arrive one by one along the time. And at each time step, we receive the user features and we have a policy to select an arm. And by pulling that arm, we received a reward from the environment. The objective of the problem is to find a policy that can maximize the cumulative reward. We adopted the upper confidence bound method, which can balance the trade-off between the exploration and exploitation during the Bandit algorithm. In terms of fairness, we consider the counterfactual fairness in this problem, which asks this question: will customers with similar profiles receive similar results regardless of their protected attributes and recommend items? So we want to achieve counterfactual fairness, which means that we want similar individuals to receive similar rewards. This counterfactual fairness notion can also be considered as the user-assigned individual fairness for the customers. In this work, we also propose to utilize a structural causal model. We consider a causal graph as shown in this figure, where A represents the features of the selected arm, and X represents the user features. R represents the reward that he received by pulling this arm, and I represents any intermediate features between A and R. So in this context, the policy can be considered as the function of A, which is dependent on the user features. Then in this work, we can similarly use software intervention to model the arm selection policy. We use a pi to denote the software intervention, which is conducted on A, while all the other attributes and the relationship in the causal graph keep unchanged. The advantages of using software intervention for modeling arm selections are, first, we are able to capture complex causal relationship. Second, we are flexible in terms of the functional form, so we are not limited to a certain functional form, for example, the linear equations. And third, the software intervention can either be deterministic or stochastic, so we are not limited to the deterministic policy only. But in this work, we also develop our algorithm based on the deterministic policies. And then, by leveraging the causal inference techniques, we can infer the post-intervention expected reward under the software intervention, which is given by this formula. And then, based on the post-intervention distribution, we can formulate the counterfactual fairness. Specifically, for each individual whose features are denoted by xt, we consider the counterfactual reward where we use an intervention to force the protected attribute of the individual to S star, while we also perform a software intervention to deploy the policy pi. And then based on that, we can formulate the counterfactual fairness as the counterfactual discrepancy by using this difference. Then it is straightforward to define a tall counterfactually fair policy, which means that a policy is tall counterfactually fair if the absolute value of the counterfactual discrepancy is less than the threshold tall. Here we have a technical challenge because in our case, the counterfactual effect is unidentifiable because, which means that we cannot compute the counterfactual effect from the observational data. So to address this challenge, we derive a closed form bound for bounding the counterfactual quantity that includes both the upper bound and lower bound. So as a result, we can also compute the bound for the counterfactual discrepancy. Based on that, we developed an algorithm called the counterfactually fair causal bandit. The main idea of this algorithm is to always select optimal policy from a counterfactually fair safe policy subspace and every round. To be more specific, at every round, we compute the estimated mean of the policy, and we also compute the estimated counterfactual reward, which is to estimate the counterfactual discrepancy, or to be more specific, the bound of the counterfactual discrepancy. Based on that, we construct the safe policy subspace. where we consider the upper bound. And then we take the optimal policy at every round from the safe policy subspace. And then according to the reward, we can update our policy mechanism. In the experiments, we use synthetic data, which combines two real-world data sets, the adult data set and the YouTube video data set. And each round, we randomly select one individual from the adult data set and recommend a video to that individual based on the YouTube video data set. In terms of the reward, we manually construct a reward function to computing the reward for each video that is recommended to each individual. And then we train our model based on this data. The results show that the model can, our model can induce small regret and at the same time achieve fair counterfactual fairness at all time steps. Okay, so let me conclude my presentation and also discuss some future direction. In this talk, I explore the fair sequential decision-making on two dimensions. In one dimension, we consider that the decision models are deployed sequentially, and in another setting, we consider that the data arrive sequentially. I show that the structural causal model can be used as a general framework for fair machine learning, and the software intervention can be adopted as a general methodology for modeling the model deployment. As for the future direction, we can consider the cross point of the two dimensions. For example, when we consider the fair multi-stage recommendation, where customers are recommended a sequence of items from different stages regarding different but related topics. So that concludes my talk. Thank you for your attention, and I'm happy to take questions.
Yeah, as Lucas said, I will be presenting random isn't always fair candidate set imbalance and exposure inequality and recommender systems. So my name is Amanda Bauer. I work on Twitter's machine learning ethics, transparency, and accountability team. And this is joint work with my excellent colleagues, Christian Lum, Tomo Lazovic, Kira Yi, and Luca Belli. So I briefly want to talk about the impact of recommender systems and how that kind of came to be. This will be familiar to everyone in the audience, but just for completeness, let's talk about it. So recommender systems historically have used the probability ranking principle. And this says that in order to maximize utility to the users or consumers of the system, the order of the items or the recommendations should be in decreasing order of relevance to the user. However, this paradigm completely ignores the producers of the items that are being recommended, whether that be content creators on social media or small businesses that are selling products on e-commerce websites. This is despite the clear economic and social impacts to these producers. For example, recommender systems can greatly influence who or who does not have access to the multi-billion-dollar creator economy. And so historically, this over-indexing on consumers, it has been shown that grave inequalities can arise with who or what gets seen. So if we want to reduce these inequalities, we need to understand how they come to be. So naturally, for non-algorithmic reasons, only a few items get exposure that will naturally lead to inequalities. For example, intentional design choices that only limit the number of recommendation spots to 2, for example. We also know that users have trust bias, where they tend to engage with items that are ranked highly regardless of relevance. Of course, users only have a limited amount of time. They can't scroll, for example, social media endlessly. So they can only see a few things at a time. And then there's user intention. If a user is searching for a web page or trying to purchase a product on an e-commerce website, they're probably only looking for one thing. And that one thing gets all the exposure or the money while the other items do not. However, now or furthermore, when we consider the algorithmic means at play, if we think of the probability ranking principle, which again says we should recommend items in decreasing order of relevance score, these inequalities become even more exacerbated because, for example, on the right-hand side, I would argue the first 5 items all have very similar relevance score, but their outcomes in terms of exposure is quite different. The first 3 get seen while the other 2 do not, despite them being kind of similar. And then when we consider that relevance scores are estimated, it just makes the problem worse since there's noise. And now these small differences that might not even be correct are being basically expanded upon. So the real problem is only one item can be first, one item can be second, and so on in rankings. And so when you use a deterministic ranking, there's a lot of rigidity in how exposure is allocated to different items. So one emerging standard solution that has come up in the literature is using stochasticity in recommendations. So for example, you would have some kind of distribution on all different rankings of these 4 items, and you would sample a ranking when it comes time to recommend someone items. And stochastic rankings give you a lot more flexibility in how exposure can be allocated to different items. So for example, you might pick a distribution that has the property that 2 items with similar relevance score get similar levels of expected exposure. So using this reasoning, you might think then if we sample rankings from a completely uniform distribution, in some sense, this should be the most fair thing you can do because every item has the same expected exposure. And this has been used as a baseline in a handful of papers, and it's very commonsensical and reasonable to do. But we argue that under a realistic scenario, uniformly randomly ranking recommendations can actually increase inequality over the deterministic baseline. So in this toy example, every column corresponds to a different user and the 4 recommendations they receive. Every letter in this table corresponds to a producer. And you might notice that producer J is overrepresented. They appear in every single person's recommendations. Perhaps it is a producer that is popular and used as backfill to make sure that everyone has enough recommendations when we don't have enough signal on them. Now, if we make the, and one thing I want to mention is in this table again, the recommendations are sorted in decreasing order of relevance score under this deterministic ranking algorithm. So now if we make the simplifying assumption that each person views only their first recommendation, we can look at how much exposure each producer receives. So under the deterministic ranking, it turns out that in this toy scenario, there is perfect equality when it comes to exposure. However, if we randomize the recommendations uniformly at random, it's a different story. And now there's variance in how much exposure each producer receives. And in particular, this popular producer, J, receives a disproportionate amount of exposure compared to its peers. So something that is very common, that makes intuitive sense that, oh, it should be the most fair thing, actually makes things worse. So what's going on? I've already kind of alluded to this, but in practice, ranking is typically a 2-step process. You have a massive universe of all the candidates. That's too big to rank, so you use some computationally cheap method to do candidate generation to subselect some of the candidates, and then you subselect further and rank the remaining ones. So a lot of the literature focuses on step 2, and it doesn't really consider any kind of inequality in the candidate generation step. Furthermore, as we pointed out in the previous example, rankings are produced for many users at many points in time. When we reasoned about uniform rankings, we did not implicitly say that this was for a single user at a single point in time, because while it is true that at that single point in time, any one of the candidates has an equal chance of being first, if we take a step back and zoom out like we did in the toy example, inequality kind of accumulates over multiple users and multiple points in time. And so there's a difference between viewing this problem on an individual ranking level, this problem being reducing inequality, or viewing it at a global level. And, arguably we care about what happens at the global level. So other than kind of pointing out this paradox, our contribution at a high level is proposing a simple post-processing algorithm to sample rankings from a class of ranking distributions. This class interpolates between producer exposure equality, or something close to it, what we'd imagine the uniform rankings to do, and maximal consumer utility, where we measure that in terms of relevance scores. We do this by leveraging global information about how often a candidate appears in all the candidate sets. So before describing our approach, we just need to take a step back and discuss an algorithm that we will build off of. So Plackett-Luce sampling is a post-processing algorithm that has been proposed in the literature, and it takes already learned relevance scores and comes up with a distribution to sample recommendations from. Every item has a relevance score, and we will transform this score by multiplying. So the scores are given by R. We'll transform this score by multiplying by beta and exponentiating the scores. And if you haven't seen this formula before, it looks a little complicated, but at a high level, what it does is for items with a high transform score, those items are more likely to be selected and ranked highly. And for items, for two items that have a similar transform score, these two items will have similar levels of expected exposure at the individual ranking level. And to understand this formula more, if you take beta to infinity, we get back the deterministic ranking. And if we take beta to 0, we end up with the uniform sampling over all rankings. So we made a simple modification to this algorithm by taking into account how many times a candidate appears in a candidate set. We denote this by this variable W. And now we transform the scores by adding the inverse of this W plus a hyperparameter. Again, there are similarities to the previous slide where the larger this transform score is, the more likely that item will be ranked highly. If two items have a similar score, they will have similar expected exposure. But now again, if you take beta and alpha to infinity, we get the deterministic ranking back. But what's a little different now is if alpha and beta go to 0, we end up just with the inverse weights. And so this means we are going to items that do not show up often in candidate sets will be ranked, will be more likely to be selected and ranked higher when they do appear, and items that are overrepresented in the sets will be less likely to be selected and ranked. So we call this approach Plackett-Luce sampling with inverse candidate frequency weights. So before we present experimental results, let's go over the basics of our data setup. So we assume for every user, there are K candidates in each of their candidate sets, and they view exactly the first L recommendations. We construct our candidate sets like in our toy example, where we select a very small number of users or candidates that will be overrepresented in the candidate sets. In the plots I'm about to show you, we compare to a few different algorithms. We specifically point out the inverse weighted algorithm, which is a special case of our algorithm where relevance scores play no role, and instead we sample just based on these inverse weights. We're trying to do what we would expect the uniform ranking algorithm to do. The deterministic ranking we've talked about. Scaled placket loose is the algorithm that we modified to make our own. Randomize is just uniformly randomizing the rankings. And PG rank is a standard, well-used algorithm that learns a fair recommender system. So we will evaluate inequality with the percentage of all views that the top 1% of candidates receive. And we will measure model performance by what we call content quality, which is just averaging the relevance score or the ground truth relevance score of the viewed candidates over all the users. So these are the synthetic results. I think without getting into the details, we just make the setup similar to our toy example, where again, there are popular candidates that are overrepresented in the candidate sets, but these popular candidates typically have a low relevance score. So under the deterministic ranking, they would show up towards the bottom, again, mimicking like what would happen in practice if you use these candidates as backfill. In these plots, you'll notice that there's a few different lines, and these lines correspond to different hyperparameter choices for the different algorithms. And so we see a few, I just want to point out some very reasonable things. The deterministic algorithm has the highest content quality measured by the y-axis, but it has a relatively high level of inequality measured by the x-axis. And then the randomized algorithm notably it's very stark that it does the worst in terms of inequality by far, and way worse than deterministic, just like in our toy example. And interestingly, it also has a pretty low content quality. This is in comparison to a special case of our algorithm, which is inverse weighted. In this case, we see inverse weighted does what we thought the uniform ranking would do. It reduces inequality substantially. It's actually the minimum out of all of these choices, and it has a decently relatively high content quality, especially compared to the randomized algorithm. I also just want to point out, based on the formulas I showed you and the hyperparameter, there is this smooth interpolation between the deterministic ranking and inverse weighted. If you choose different hyperparameters, both this orange and blue curve are our algorithms, and it makes sense that it interpolates between these. Similarly, for scaled placket loose, we see this interpolation that again makes sense as we discussed what happens when these hyperparameters go to infinity or go to 0. So I think the big key takeaway from this plot is that for our algorithm, which is in the blue and the orange triangles and blue stars, it either performs the same as the scaled placket loose baseline, or it significantly outperforms it in a particular regime. We clearly reach the lowest level of inequality. And another takeaway is like looking at how poorly the randomized algorithm performs. Now I want to present some real data experiments. So this is the German credit experiment. This is a well-studied and used binary classification data set that in fair ranking context is usually repurposed as a ranking data set. In this case, we learn the relevance scores, and now we're also comparing to an in-processing algorithm, PG rank. I'm not going to repeat some of the reasonable things we saw last time, like deterministic having the highest content quality, but I think a couple differences here is that randomized now does better than deterministic, but it still has a relatively high level of inequality, especially compared to the inverse weighted one. And in this case, for inequality greater than 20%, we see that our approach is slightly outperformed by a couple of the baselines, but once we get beyond smaller than 20%, our algorithms are outperforming PG rank and also scaled placket loose. And so A few key takeaways from this talk that I hope you all get is that common sense solutions to fair ranking can behave unexpectedly when candidate sets are imbalanced. And so this is important as practitioners when we're taking methods off the shelf. We really need to consider that some candidates may be overrepresented. And then of course, we propose a simple, computationally inexpensive post-processing algorithm that can interpolate between consumer utility and producer side exposure and close to producer side equality of exposure. And we showed that these approaches worked on synthetic and real data sets. So thank you. I'm happy to take any questions.
So hello, everyone. My name is Alan, and I'm a second-year PhD student studying at Texas A&M University. I'm really glad to be here to talk to you on fair conversational recommender systems. I will first start by providing a brief background on what a conversational recommender is and why it's exciting. So when making a new recommendation to users, a traditional recommender system typically infers from users' past purchase history or interactions to come up with new items that the user might take. Like in this example, since Bob has had frequently purchased iPhones in the past, it's likely that a traditional recommender system would recommend more iPhones to him. However, past interactions or purchase history do not necessarily encode in a user's current interests. So in this scenario, after 2 iPhones in a row, Bob has become a little disappointed and would like to try some Android phones. But limited to only past purchase history, it's really hard for a traditional recommender to overcome these two fundamental challenges. One, it's hard for a traditional recommender to figure out what exactly the user likes, since historical interactions might fail to represent one's current interest, as preferences might have shifted over time. And 2, it's really hard to really justify or explain the reason of why certain items were purchased versus why certain items were not. So to solve these challenges, conversational recommender systems have been proposed. So by directly eliciting the dynamic preferences of users through multi-turn interactions, a conversational recommender system can provide recommendations that are both highly personalized and justifiable. But now comes the question, do personalization and justification guarantee fairness in recommendations? As many works have shown, traditional recommender systems are subject to various types of biases. For example, one of them is popularity bias. So in this scenario here, since the white and the black iPhones have had many purchases in the past, a traditional recommender system could overly recommend these popular items at the expense of the unpopular items, such as the Google Pixel phone. And this is when even when these 2 items could be essentially equally qualified merit-wise. And also we have exposure bias, where popular movies tend to get overly exposed to viewers at the expenses of unpopular movies, even when it's a movie that the viewers would actually love, like in this case, The Sixth String Samurai. Now, back to our key question earlier, do personalization and justification guarantee fairness? I mean, on one hand, one could argue that conversation recommender systems only recommend items that perfectly match the specified criteria or preferences of the user. So there's no way bias could manifest in a system. However, surprisingly, recent works have shown that conversational recommender systems are also plagued by biases, much like traditional recommender systems. So in our recent work, which will be published on CIKM 22, we performed data-driven analysis to exhibit the existence of popularity bias in conversational recommender systems from 3 different perspectives: the exposure rate, the success rate, and the conversational utility. Now, first let me introduce the exposure rate perspective. So a conversational recommender system typically starts by collecting a set of user preferences to form a candidate item set, and then recommends the top n ranked items from that candidate item set to the user when the system thinks enough information has been collected. So here we refer to all the items that perfectly match all the specified preferences of the user as the candidate set items, and the ones that actually get exposed or recommended to the user as the recommended items. So, and in this figure, we have the x-axis representing the specific conversational recommender models, and the y-axis representing the average popularity of the items in the item set. So I mean by item set, this would either be a candidate item set or the recommended item set. So as we can see, the average popularity of items that get recommended by CRM is almost 8 times higher than the average popularity of items in the candidate set. And similar patterns observed in both EAR and SCPR. However, in a completely unbiased CRS, since both candidate set and the recommendation set contain items that perfectly match all the preferences specified by the user, the overall average popularity from both sets should not deviate too much. Now, let's examine the popularity bias from the success rate perspective. Well, let me first define what I mean by success rate. So success rate is a metric that's widely used in conversational recommender systems. It indicates how likely a ground truth item will get successfully recommended by the conversational recommender system within a predefined number of interactions. So ideally, in a completely unbiased system, an item's popularity should be completely irrelevant to its recommendation success rate. And any correlation, either positive or negative, is an indication of popularity bias in the system. Now, as we can observe from the figure, pretty much all three models exhibit strong positive correlations between an item's popularity and its recommendation success rate. For example, in EAR, items with popularity greater than 0.01, which is the 75th percentile of the sorted popularity of all items, have over 75 recommendation success rate. This means that items with higher popularity have much higher chances of being successfully recommended than items with lower popularity, and this is extremely problematic. Last, let's examine from the conversational utility perspective. And what I mean by conversational utility is that, as mentioned in previous slide, a conversation recommender is only allowed to interact with the user for a specified number of turns. And this is because in reality, too many interactions could easily cause the user to lose patience and just quit the system. Therefore, items requiring fewer turns of user interactions to get successfully recommended should be considered more advantageous than those requiring more. And this is because the less interactions means less chances of the user becoming impatient and quitting the system. And this is the rationale behind conversational utility. So essentially, conversational utility measures how much effort is needed from the user to get a ground truth item recommended. So intuitively, in an unbiased conversational recommender system, an item's required turns of user interactions should be completely independent of its popularity. However, as shown here in the figure, all three models pretty much exhibit strong inverse correlation between an item's popularity and its required turns of user interactions, meaning that items with higher popularity would actually require less user interactions to get successfully recommended, meaning items with higher popularity actually have higher conversational utility. And this is problematic too. So, so far we have shown that biases in traditional recommender systems could also manifest in conversational recommenders. But do conversational recommenders alone introduce new types of biases? Well, unfortunately, yes. So in the following slides, I will introduce two types of biases that are unique to conversational recommenders. First, let's look at the user preference assumption bias. So a conversational recommender starts by prompting users with questions to collect their current preferences. And this process is called user preference elicitation. And then this recorded user responses or feedback then used to help the system make more personalized recommendations. So user preference assumption bias refers to the phenomenon that the user preference elicitation process is heavily dominated by the system only asking the user preferences on a small subset of the entire domain-specific attributes. Well, take cell phone recommendation as example. Since the attribute memory size can quickly narrow down the candidate item space, the conversational recommender would assume that every user has a strong preference towards specifying the memory size of the phone. However, in reality, this might not always be the case. And next, we have the evaluation bias. So to evaluate a conversational recommender, many previous works have adopted success rate as the evaluation metric. So essentially, success rate measures if a system is able to recommend the ground truth item within T interactions with the user. So while this intuition seems reasonable, this metric does not evaluate the system in an unbiased fashion. So just from the definition, we can see success rate is defined as the number of successfully recommended items within T interactions divided by the number of total items. So assume we only have two users, Alice and Bob. Alice is extremely active and has 90 ground truth items in the testing set, while Bob only has 10. Now consider two scenarios. Where scenario A, the system successfully recommends all 90 items for Alice and 0 for Bob, versus in scenario B, the system successfully recommends 81 items for Alice and 9 items for Bob. Now, the success rate at T will be identical in both scenarios. However, from the fairness perspective, scenario B provides much better results than for both users than scenario A. So in summary, in this talk, we have shown that conversational recommenders are also subject to the undesirable effects of biases, much like traditional recommenders. However, what's different is that conversational recommenders alone introduce new types of biases that were further studies. And here comes a challenge for the community. Even though we have proposed a framework to mitigate popularity bias in conversational recommender system, there could be other types of biases that require further investigation. Can the same type of bias that exists in traditional recommenders be addressed in a similar fashion in CRS? And if not, what changes are needed? Also, do conversational recommenders introduce new types of biases other than the ones mentioned? If yes, how should they be measured and mitigated? All right, this concludes my talk for today. I will be taking questions. Thank you so much for listening.
Okay, hello everyone. My name is Masoud Mansouri. I'm a postdoc at the University of Amsterdam and also a member of Discovery Lab at Elsevier. So I'm happy to present my work on exposure-aware recommendation using contextual bandits, which I studied. Actually, we studied the problem of exposure bias in dynamic recommendation setting. This is a joint work with my colleagues from DePaul University and University of Amsterdam. So it is well known that recommendation algorithms suffer from different types of biases. One of these biases is exposure bias, which we just mainly focus in this research, and mainly refers to the fact that items and suppliers are not equally represented in the recommendations. For example, few popular items are over-recommended, or maybe majority of other non-popular items are under-recommended. So besides this issue of disparity in the representation of different items in the recommendation list, exposure bias, if not mitigated, can also be amplified over time. And it would lead to bias amplification, which in long run, it can also lead to other issues for the system. So this bias amplification is due to feedback loop phenomena in recommender system, which refers to the fact that users and recommender systems are in a process of mutual dynamic evolution, where, as you can see in diagram, users interact with the items and build the training data. Then this training data would be used as input for recommender system. Recommender system processes this training data and then generate recommendations and deliver to the users. Then users interact with the recommended items and maybe select or click on some of the recommended items. And those interactions would be also added to the training data, which would be used as input for recommender system in the next time step. So in this, this way, user and recommender system form a feedback loop, which, as you can see here, recommender system. So in this process, recommender system induces bias through recommendations, and also recommender system is the element here that determines how much exposure should be given to each item. And as you may know, exposure has, direct influence on the economic gain for suppliers of different items. So it is important to understand how we should expose items to the users in long run to avoid bias, to also fairly distribute the total exposure to different items belonging to different suppliers. So in this work, we try to answer these three questions. First, we try to introduce metrics for measuring exposure bias in dynamic recommendations. Second, we try to analyze some of existing recommendation algorithms, those that are designed for dynamic recommendation setting, in order to be, the ones that are working over time. So learning through interactions with the users. And also the third question is how we can modify these algorithms to further improve exposure fairness in the recommendation results in long run. So the first question, we want to understand what types of metrics we can introduce in order to measure exposure bias in dynamic recommendations. So for this purpose, first we need to understand how we should measure exposure of each item in long run. So when the system is operating for T iterations, so the question is how can we compute exposure assigned to each item in this period. So we propose two definitions for exposure here. First is position-based exposure, which is a combination of, this function, which returns 1 if item I appeared in the recommendation list of user U, and otherwise it would be 0. And the second term here is the weight term, a well-known position drop-off, which assigns weight to different position of the recommendation list. So positions on top of the list would get the highest weight, and position at the bottom would receive the lowest weight or lowest exposure. So here we just try to cumulatively compute the total exposure given to different items. For example, for item I here, through all the iterations, and for each user, we just sum up all the exposure we assigned to this item I. So the problem with this definition is that it assumes that all the items that are recommended are getting exposure. But the fact is that sometimes we recommend some items, but those items may not get any exposure because, for example, the user may start examining the items from the top of the list and one by one to, for example, to the bottom. So it is possible, for example, the user stops examining the items after position 5. So those items at the bottom of the list, even though those items are recommended, but are not, examined by the user. So this means that there is maybe no exposure for these items because these items are not seen by the user. So the second definition is position-based examined exposure. So it has the same computation, but here we just changed the upper bound for this sigma is changed to mean of position of the clicked item, and the size of the recommendation list. So if user clicked on an item, then stop examining the rest of the items. So those items are getting no exposure. So this definition is position-based exposure, examined exposure. So these are the definitions for the exposure. So based on this exposure definition, we have exposure value for each item, which we can form a distribution of exposure for the, so after, for example, 3 rounds of recommendation. So now we can introduce metrics for measuring exposure bias. The first metric is equality of opportunity. So it is the Gini index computed over the distribution of exposure derived by the first definition, position-based exposure. So the second one is equality of impact, which is the Gini index computed over the exposure distribution derived by position-based examined exposure, the second definition. And the last metric, which is the simple metric, which is the fraction of items that appear at least once in the recommendation list of T rounds. So we run the system for a long period, and we just want to, is there any item that that is not shown in the recommendation list at all after this long period of running the system? So these are the metrics we introduced. The second question is how existing algorithms handle exposure bias. So to answer this question, we performed sets of experiments, and we performed our experiments on these algorithms. These are well-known algorithms on linear cascading bandits, which we will talk about the internal of these algorithms in a few slides. So these are Cascade Lin UCB, Cascade LSB, and Cascade Hybrid. And for data set, we use Amazon Book and MovieLens data set. And for simulation, we use 50% of user profile for training, 50% for test. Experimentation are performed for 50,000 iterations, and also recommendation list of size 20 are delivered to the users at each iteration. Now we can look at the results of our experiments. So in these results, so column-wise, you see the result of the results using each algorithm, each linear cascading bandit algorithm, and row-wise, you see the results on each data set. And so in each plot, you see the items versus the exposure computed by position-based exposure. So for the item. So in this plot, we can see 3 different patterns. So the first pattern is the item coverage, which in all of these cases, as you can see, there is no case that we see 100% coverage. So even though the system was running for a long period of time, we see that certain items are completely out of the market, even though we have, some interactions on those items in the training data. Another pattern here is that in all of these plots, the distribution is long tail. It means that some items are frequently recommended, frequently shown in the recommendation list, and some other items are rarely shown in the recommendation list. But this may not be, we cannot judge by this pattern, we cannot judge if there is any exposure bias or not, because one may say these items that are frequently shown in the recommendation list are because those are the higher quality items, and recommender system just recommended what users liked. But if you look at the third pattern, if you look at the color bar here shows the false positive rate, which is the number of times item I was recommended but was not clicked divided by the number of times item I was recommended. And the red color shows the high false positive rate, blue is the low false positive rate. As you can see, there are cases where some items, even though those are not picked by the user, those are not clicked by the users, but recommender system repeatedly just recommend those items to the user. So the user did not select those items, but those items are over recommended, over shown to these users. So these 3 patterns overall can signify sign of exposure bias when the system is operating over time, and the exposure is not fairly distributed among different items in long run. The same patterns can also be observed based on position-based examined exposure. So I'll skip this slide, but the patterns are the same. So the third question is how we can modify these algorithms to improve the fairness of, exposure fairness of these algorithms. So to answer this question, first we can look at the internal of linear cascading bandits. So this shows the general structure of contextual bandits for top K recommendation, and assume that X is matrix of item embeddings, which is known to the algorithm. Theta is the embedding vector for a user, which is unknown, and we want to learn it through interactions with the users. So inside the loop at each iteration, we observe context. So in observing context, we know that dot product of the item embedding with vector of user preferences or user embedding is the attraction probability, how much user is interested to different items. So in this equation, X is known, item embedding is known, and attraction probability is known as well. It's the user feedback collected, from past iterations. So here we can just derive theta using, solving a ridge regression problem, which is this term. And we just say M is, this term, this part, which is the covariance matrix of item features. And this term, we call it B, vector B, which is the importance weight assigned to each feature of the items. So in the next step, we need to generate the recommendations to the users. So we need to compute a score for each item and then return the K items with the highest score that we computed here. So for computing the score in these algorithms, upper confidence bound is employed, which computes the score based on combination of attraction probability and the upper bound for the estimation of this theta. So in this way, we compute the score and then we deliver the recommendations to the user. In the third step, we observe the click from the users. And in the last step, we need to modify our model parameters based on the feedback we observed from the user. So here, so matrix M is updated by adding, this term to it, and and vector B is updated by adding this term. So here, matrix M is updated for all examined items, but vector M is so vector B is updated only for the clicked items. Just, feature of X is added to vector B based on the clicked item. But the problem with this formulation is that all the items, no matter in what position they are clicked or are not clicked, all the items are equally penalized or rewarded. So what we claim here is that we need to incorporate positional information of the items in the reward model. So if the item is recommended on top and clicked, then it should be slightly rewarded. But on the other hand, if the item is recommended at the bottom and clicked, then the item should be significantly rewarded. And the same for the unclicked item. So we just change this equation by adding this term to it, this function f. And function f is computed this way. For all clicked items, we just reward that item by this amount. And for all unclicked items, we reward it by this amount. And K here is the position of the item that we want to reward or penalize. And lambda here, gamma here is the hyperparameter that controls the degree of penalization. So this is our modification to the algorithm. Now we can look at the results. So this is the results based on the best performing hyperparameter setting for each algorithm. And EA here for each algorithm here shows our proposed model. We can see that click, so based on the click, which is as a kind of accuracy of the system, we see that in most of the cases, our proposed, modified version of the algorithm obtained higher clicks. So higher clicks is observed when we take into account the positional information of the items when rewarding or penalizing them. And also in terms of exposure bias, in almost in all of the cases for both data sets, we see that exposure bias is significantly mitigated compared to the original algorithm. Also, we did some experiments in terms of mitigating bias amplification. So in terms of equality of opportunity, we computed equality of opportunity up to each round in our experiment. So here in the round 20,000 here, we computed equality of opportunity, and we see that over time, as the system operates over time, we see bias is reducing compared to the original algorithm. And the same pattern is observed for equality of impact. And in conclusion, we studied the problem of exposure bias in linear cascading bandits, and also we observed that these algorithms fail to provide a fair chance for different items to appear in the recommendation list. So we proposed exposure-aware reward model that showed superior performance in terms of improving exposure fairness and also maintaining the accuracy of the system. And in future work, we also plan to extend our analysis to other notions of fairness, like so those based on equity of exposure. Thank you for your attention, and I'm happy to take any questions.
Hi, I'm Ashley Melton. I am a PhD student at University of Minnesota working in the Group Lens Lab. And today I'm presenting on a position work regarding the propagation of harmful mental illness behaviors through recommendation systems. So just a little bit of context, users are being subjected to recommendations in pretty much everyday life now. And usually this is a very positive experience. Recommendations are fulfilling an inferred need these users have. But there's also the ability for recommendations to not be so positive and to actually be harmful and present ideas or content to users, particularly at-risk users like those with mental illness, that can be negative behavioral actions. And so when I'm talking about recommendation harms in this paper, we're talking about recommendations that a recommendation system providing content or ideas that would exacerbate existing mental health symptoms or would be negative mental or physical effects on these users. And the question then is like, well, is this actually happening? And so what I did is I went out into the great wild of active recommender systems and saw if I could find any examples of these negative effects. And so here's where I want to put a disclaimer. Going into these examples, I will be touching on topics of self-harm, suicide, eating disorders, and extreme dieting. If you are sensitive to any of those topics, please feel free to just wander off for a couple of minutes. I just want to put that out there in case anyone is sensitive. And with that, we'll jump into the examples that I found. And so this first one is blurred for reasons. This is what I'm calling chemical A and chemical B that is being recommended on Amazon. Now, both of these chemicals independently are not harmful. They're both used for various reasons. However, when they are together, they are actually a very potent suicide cocktail that actually keeps the body from having its reflexive self-preservation response, and therefore increases the likelihood of a suicide attempt succeeding. And so for obvious reasons, this seems like it is a harm that the system is pushing out onto users. Now, not all examples are this, I guess, obvious. The next one we have here is a more subtle example. So this is the recommendations associated with some caffeine pills. The recommendations alongside it are an appetite suppressant and a weight loss pill. Now, this might seem logical, but caffeine pills are actually predominantly used by people with eating disorders. And so you have a user that may be looking at this who has an eating disorder, is going for extreme weight loss, and is now also being subjected to the idea of appetite suppressants and weight loss supplements. And to pack onto this, none of these supplements are actually reviewed by the FDA, and there is no pharmaceutical oversight over them. And so we don't even know what the combination of these taken together would even do to a person physically, let alone the mental effects of actually being shown these in a recommendation system. And while the ones that I've shown so far are from e-commerce sites, this is also something that we see in social media. And so there was something called the Blue Whale Challenge that started back in 2016. If you're not familiar with what this challenge is, it was a social media challenge where administrators would assign tasks to users over the span of 50 days. The problem is those tasks progressed into having elements of self-harm, with the last task actually being for the user to kill themselves. Now, this actually went viral on YouTube and Twitter, both social media sites that have a very predominant recommender system associated with the platform. And what was found to be happening was, even within the comments and how both of these sites were pushing this content, it was creating a contagion effect and actually glorifying this harmful behavior and pushing it out to at-risk users, who then, due to the contagion effect, started having the suicidal ideations. And so this is the last we're going to deal with the heavy topics, and now we're going to go into the questions. So obviously we know now that these harms exist. So how can we actually keep users safe when they are dealing with recommendation systems? And the two big questions that came across in thinking about this were, could recommender systems consider a user safety when they are presenting their content? And who should be held accountable for user safety, and how are we going to hold them accountable in these situations? And so in looking at recommenders actually considering user safety, we thought that there was like 3 places where future work could kind of dive into and see if we can get this accomplished and get these harms mitigated. One is data. So it's a high likelihood that these behaviors are coming from a user, probably an at-risk user. Would it be possible to catch these before they get propagated through the recommendation system and basically pushed out to other at-risk users? Now, there is some work in detection of suicidal ideation and mental health in social computing. However, there's a lot of ethical considerations that would need to go into using something like that. That is already being talked about in social computing. So before we would bring it into recommenders, we really need to think about how we would want that intervention to go. Second is context. So from the second example, we talked about it was a combination of items. And so could recommenders think about, well, should there be a combination of items here? How do these items actually interplay with each other? And how would that affect a user? The other one is, should items actually be eligible for recommendation? So from the first example, chemical A in and of itself is known to be detrimental to user safety. And so should that item even have be able to be recommended? And last is evaluation. A lot of the evaluation that we focus on is on performance. However, performance isn't going to catch a lot of the stuff that came through these examples, but people have been doing stuff with simulation in other domains. And could we simulate different use cases for these users in recommendation systems to try and head off some of these harms? The second question is, who should be held accountable? And so looking at this from an author or a research perspective, some conferences have been asking for broader implications, which asks authors to actually consider the ethical standing of what their systems are doing. But it would need broader adaptation. And second is legal consequences. And so the first example, Amazon got into some interesting legal situations with that, where it actually got pushed all the way up to the US Congress. And so there is a precedence for there to be legal issues as well as civil ramifications, because there's also lawsuits associated with that because people did lose their lives. And so clearly there's harms that exist for our at-risk users. We really need to consider these harms and how to mitigate them so that we can make recommendation systems safe for users with mental health issues. And with that, thank you for listening.
Anyway, yeah, thanks for the introduction. So I'm here to present this joint work with my colleagues Bhaskar Mitra and Sean Lindley. And yeah, we already said the title. I'm not going to repeat that one again. If I can just get it to, yep, great. So Bhaskar, Sean, and I work on Project Alexandria, which is a research project within Microsoft Research. And Project Alexandria uses probabilistic programming to extract business knowledge from an organization and structure it into a knowledge base. And this is used in a product called Viva Topics, where the extracted knowledge is automatically structured into topics. And so Viva Topics associates people and documents with these topics, so kind of like Wikipedia pages, but within a company. And these people and documents associated with these topics or Wikipedia pages are then based on, their document content or the editing patterns of these people. And what you're seeing here is a mock-up, so it's not a real example from a knowledge base. But as you can see from the example, people appear fairly prominently in this product. And these topics or pages are surfaced in people's work along with these pinned people and these suggested people on the topics. And they're surfaced, for example, through highlights that open up these kinds of little info cards. And so our precision paper addresses concerns around what consequences it can have for organizations and their employees when a system recommends people as experts on particular topics. So we address 5 categories of concerns in our paper, and I'm sure they're familiar to many of you to a greater or lesser extent, but what we've done is then discuss them in the context of knowledge bases and recommendations within an organization. And so I'll give a summary of each of these concerns and how they relate to these organizational knowledge bases. So the first one, erasure, refers to practices and actions that render certain individuals and groups invisible. So for example, by not acknowledging their needs in the implementation of systems or in organizational protocols. And the result of this can be marginalization or exclusion. And in the case of organizational expert recommendation, the way the machine learning system infers expertise influences who will then be acknowledged for their work and how. So for example, with a system that looks primarily at textual document content, people who write long reports will appear to contribute more than people who primarily create UX designs or who do a lot of programming, for example. And so the result of this could be that certain people do not receive the same recognition for their work as their colleagues. And one of the questions we think that we should then be asking to mitigate this is what content and data is needed to adequately represent expertise in a given organization or domain or across multiple domains. Another concern is the amplification of existing biases. So this can, for example, happen when recommendations are ordered by slight differences. So as people have already talked about today, actually, so if there's a slight difference in the estimated relevance of a person or the estimated expertise, this might manifest in the way they're ordered on a list of recommended people. And research has shown that people tend to engage disproportionately with the top recommendations, which results in vastly higher exposure for the top recommendation, even if secondary recommendations are estimated to be nearly as relevant. So if the ranking or relevance or expertise is only slightly biased, which is highly likely in some way or another, then these kinds of patterns will amplify that bias. And so in addition to effectively reducing the organizational visibility of the experts who fall in second place or below, this can also have consequences for the person who is identified as the top expert. So when they're more often put on the spot as the expert, it may, on the one hand, provide them with additional opportunities to connect with others and develop their expertise. But on the other hand, it may take time away from their work and their chances to develop other areas of expertise. And so there are ways to address this in the design of these systems. Also, some people here have already presented relevant explorations and solutions, but we need to ask what the right balance is between striving for the highest possible estimated relevance or expertise and sort of surfacing content that diversifies organizational and individual outlook on expertise. So that's sort of another angle to add to these more technical solutions. And then another topic is perverse incentives. So if people are aware of the way that traces of their work actively influence how they appear in the organizational knowledge base, quite a natural response might be to adapt the way they work to ensure that the system picks up on the things they wanted to pick up on. Or similar to Goodhart's law, the system's measures of activity might end up becoming the target for people's activities. And so with these dynamics of perverse incentives, there is a risk that work culture becomes focused on the way work is performed rather than on the long-term value of one's contributions. And this also risks producing a culture where people perform extra work without being compensated for it for the sole sake of maintaining their visibility and ensuring that they get the credit that is due for their work. And so to address these risks, we have to examine the organizational knowledge base and the way in which it's used, and ask what forms of knowledge production are indirectly encouraged or discouraged by the system. Knowledge bases like Viva Topics are active in the sense that they directly encourage people to explore topics and reach out to people. And this means that they actively influence and shift the way people use and produce knowledge. So the identification of expertise is part of these knowledge practices, and it has always been mediated through social connections in situated or contextual ways. So before these kinds of systems, it would just be that through my network, I would find out who's the right expert for this problem, and we would experience trust building in this expertise through the work that people do. But classification systems, as knowledge bases are, tend to codify experiences in more rigid ways. And so when we slot these more rigid systems into soft knowledge practices, we need to ensure that we're enhancing and not ruining the practices that work well. So we have to ask what consensus building and trust should look like when automated knowledge bases and recommender systems become key infrastructures for work. Finally, the last category of consequences relates to the well-known phenomenon where technology embodies the values of those creating and using it. So in the case of systems that collect and surface organizational knowledge, they will reflect existing power structures and discrepancies in the workplace and potentially invite abuse of power. So a current hot topic of discussion is micro-monitoring of employee productivity, or bossware. And this can reduce the agency of employees to carry out their work in the way that works best for them. And so we have to ask what kinds of accountability, new forms of visibility impose on the people whose activities are being mined and displayed through the system. And essentially, or especially, what risks of power abuse this might introduce. So there are many more questions to ask, including who should influence and control the construction of organizational recommender systems at various stages from design to adoption and use, and who owns the knowledge extracted from activities and work, and also what does it do to a person's ownership of a process or a work process if that work process is modeled and made replicable for other people. And what would be the pros and cons from an end user perspective of being given control over how one's work data is interpreted and when it's used? So this paper is our first step towards a deeper engagement with these topics, and we have only just begun to speculate about how the potential issues of developing active organizational knowledge bases might unfold. So as a final point, we would like to stress that no vision for the future of work is complete without adequate emphasis on the future of workers. And to support this emphasis, the more technical work behind knowledge-based construction and recommender systems needs to join forces with human or worker-centric approaches, such as participatory design and the work being done by labor movements. And that was it. Thanks for listening.
A lot of us today have spoken about preferences. So the interesting thing about preferences is in the literature, they get defined in a lot of ways. And to my knowledge, this is mostly because some people define them conceptually while other people use operational definitions. So I want to start off with proposing a definition of preferences. This is work from a previous paper, but when I talk about preferences, I'm defining them as any explicit, conscious, or reflective, or implicit, unconscious, and automatic mental process that brings about a relative ranking of options or a sense of liking or disliking for something. So what this definition allows us to do is it allows us to broaden the scope of preferences and take a sort of like reductive approach that allows for the inclusion of all other cognitive psychological processes. And these cognitive mental states are those which aim to bring about something in an environment rather than describe it. This is how they're different from cognitive mental states. Now, preferences in behavior have a bidirectional causal relationship. So, often when people think about preferences, they think about something that sort of reveals itself in behavior. And in economics, this is called revealed preference theory. But actually, one's behavioral history can lead to the emergence and the formation of new preferences. And this becomes a problem due to the iterative nature of machine learning that is used in recommender systems. So machine learning systems learn preferences and change the interaction with a human in line with those preferences. This change in interaction then in turn influences human behavior. As many machine learning systems influence human behavior, they also influence human preference. So by learning preference over time, the AI is changing preference over time. People have proposed many solutions to this. So in the first study, Everett et al., this is work over at DeepMind, serving content to a user using a preference set based on counterfactual world where the user had not interacted with the system that manipulated it, removes the preference manipulation incentive. In the second study, they used this approach where they penalized the recommended systems if they shifted the preferences in a way that is sort of like unnatural or, defined as, something that wouldn't have happened if they didn't interact with the recommended system. And in this final study, they took a more sort of like a causal analysis approach where they analyzed the causal path that may cause preference change and prevented an algorithm from using elements of that path as a means to an end. Our problem with these sort of proposed solutions is that they're unsatisfactory because they don't take into account people's meta preferences. They assume that all changes in preference are undesired. Now, I think it's fair to say that a lot of changes in preference can be seen as manipulative, but that's not as to say, it's not the same as to say that they're undesired. A recommender can promote a preference change that is a welcome one, right? So a recommender can bring value in the form of changing our preferences. The only way to disentangle welcome shifts from unwelcome shifts is by learning about a user's meta preference. Causal analysis alone won't cut it. So we define meta preferences. So a person will have preferences that conflict with each other. And that person will have preferences over which one of these should win out and at what cost. And these preferences over preferences can be termed meta or second order preferences. And although meta preferences can be changed the same way a preference can be changed, they're far more stable. So here in the table below, you can see an example of like what a meta preference is. So for instance, someone can have a preference that makes them like something, but a meta preference that makes them dislike their liking of that thing. And in everyday language, we would call that a guilty pleasure. So I hope that in this example, I sort of showed how these two sort of things are different. So what we're arguing for is that if a recommender system were to understand how any recommendation were to change the preference of a user, it could be able to ask that user before serving it the content, whether the user was comfortable with that change. And by doing so, the recommender would be able to respect the meta preferences of that user and their autonomy. Would this end manipulation by recommender systems? No, not necessarily. The recommender system could potentially learn how to change a user's meta preference, but current psychological research shows that this is much harder to do than changing people's preferences. This is a far easier thing to do. So what we argue for is a meta preference elicitation method. So recommender engines could tell users what they currently think a user's preference is. They can use XAI methods such as example-based explanations where they give users an example of historic situations such as film they've watched in the past to tell them why they're sort of making the current recommendations that they're giving. So we're recommending film A because you've watched film B. And this could serve as a meta preference elicitation method. A user could choose whether or not to learn preferences and whether it is in line with their meta sort of preferences. So is it that they learned a one-off case, or is it something that is sort of more overall a part of their preferences and meta preferences? So it is our position that learning a user meta preference, a recommender system could better align with what the user wants with still respecting their autonomy. Preventing a recommender from causing users' preference to change is not desirable because in many situations, the change preference is welcomed. So thank you very much.
So thank you for introduction. I'm very happy to be able to talk to you today. I'm Rick Togashi, and I'll be presenting about fair matrix factorization for large-scale recommender systems. So this work was done at Cyber Agent Lab in Tokyo with my colleague Kenshi Abe. So first, I'd like to quickly summarize this work. We motivated by the fact that it is challenging to optimize recommender systems under a fairness constraint, which requires controlling the exposure of items in rankings. As a scalability in fairness-aware methods are important to solve real-world fairness issues, but somewhat unregarded. To our knowledge, there are few scalable methods for fairness survey item recommendation due to the optimization inefficiency, which we discuss later. In this work, we developed a new method for fairness survey collaborative filtering for large-scale applications called FAccTRec. So we built it on the top of IALS, which is the most efficient method for item recommendation from implicit feedback. Our method includes a fairness survey objective and optimization algorithm. So before explaining the optimization challenge in the fairness survey recommendation, I'll go over the scalability of the traditional IALS a little bit in detail. The important characteristics of IALS are mainly two parts. First one is its point-wise squared loss, and the second one is alternating optimization strategy. So the objective can be decomposed into three quadratic terms. The first term is the total loss over the observed part of the feedback matrix R, which is usually very sparse. And there's a second term, which can be considered as the expected loss over unobserved entries that pushes all predictions towards zero. So, and there's a third term, this is the sum of the square layer to norms of the latent factors for regularization. So the main tricks in IALS is its alternating optimization strategy to solve the non-convex optimization. In IALS, we first update the user-latent factors by fixing those for the items, and then update the item factors using the fixed user factors updated in the previous steps. So looking at the update step of user factors, you can notice that the optimization problem can be decomposed into the row-wise independent sub-problems. So here UI is a factor of user I, and observe that the objective for UI depends only on UI itself, right? So, and does not include the other user factors. This independence means parallelizability of optimization for users. So obviously it is analogous for the item side due to the symmetric objective, and therefore IALS is scalable with respect to the number of both users and items. So in addition to this, IALS exploits the feedback sparsity, which is usually holds in large-scale applications. The update formula of one user factor can be given by the closed form solution by solving a simple linear system. And the possible bottlenecks are in the computation of the Gramian matrix of all item factors, and that for the user's positive items. So the full Gramian matrix GB requires a linear computational cost of the number of items, and we cannot compute this for each user. But it is a constant with respect to the user. And so we can compute this only once and reuse it for all sub-problems, right? So the Gramian matrix for positive items for user is not costly, since users interact with a small proportion of items. So for these reasons, IALS achieves quite efficient complexity for a single step that is almost linear with respect to the number of users or items. So we have an illustration of workflow of IALS for a single step or a single epoch. Before the parallel update step of user factors, we compute the full Gramian matrix and distribute it for each worker that solves the optimization for users. Then synchronize the workers and compute the user full Gramian matrix using updated values for the update step of item vectors. So keeping this scalability of IALS in mind, I want to review the inefficiency issues in the method of fair ranking. The prevalent formulation in fair ranking is the form of post-processing. That is, assuming given user preferences on all items, a method aims to optimize the allocation of the ranking to the items. So the problem is formulated as a convex optimization over the set of doubly stochastic matrices for users. A doubly stochastic matrix is used as a soft representation of ranking or allocation of items to each rank position. So we can obtain the fair stochastic ranking policy by maximizing the total user utility on the feasible set of fair rankings. So however, such a formulation requires a severely large memory space, particularly for a large item set. due to the doubly stochastic matrices for users. So moreover, post-processing approach inevitably requires the preferences of all user item pairs. For example, in the case of MF, this implies a complete recovery of the predicted feedback matrix, which has been avoided in practical situations. For example, in the item retrieval for ranking, we usually avoid the exhaustive scoring by using approximate nearest neighbor search. So the cost for this is usually prohibitively large, even for simple matrix factorization. So finally, the convex optimization on the probability simplex of items usually leads to the severely high complexity for a single iteration step. This is typically linear with respect to the number of items per user, even with the efficient Frank-Wolf algorithm, which is often used for this recently, but this is infeasible for large-scale applications with many users and many items, right? So there is a really large room for improvement in terms of scalability in fair recommended systems. But this approach seems to be piled up with a lot of challenges for achieving a deployable method at this moment. So we take a different approach. To exploit the scalability of IALS, we built a method on the top of it. We just introduce a fairness regularizer into the objective of IALS. Pretty simple, right? So, but because as IALS achieves high parallelizability owing to its simple objective, and the question here is that, is there a tractable fairness regularizer which maintains the scalability of IALS? So because the loss function of IALS involves with score space, predicted score space, rather than rankings or probability simplex, we also designed the fairness regularizer based on the predicted scores. So our idea is use the variance of the average preference scores of each item as the inequality of the predicted scores. So the average of preference scores of an item can be viewed as predicted merit. So this regularizer is quadratic and differentiable, so seems compatible with the IALS objective, right? However, the mean predicted merit in the variance breaks optimization independence completely because it involves with all model predictions and so all model parameters. To avoid this intractable factor, we further simplify the fairness regularizer just by dropping the mean predicted merit. This leads to an upper bound, which can be thought of as the L2 norm of predicted item merit. So we use it as the proposed regularizer. But it still breaks the independence between users. So looking at the square of item merit, it uses all user-related factors and thus loses scalability with respect to users. So still something must be done. How did we take a step at that? The first step is to decompose the row-wise and column-wise dependency of user factors by introducing an auxiliary value of S representing the average user factor. We can reformulate the original 2-block problem to the 3-block optimization with a linear constraint. Alternating direction method of multiplier is an optimization algorithm for solving such a multi-block constraint convex problem. So ADMM is a multi-block extension of the Lagrangian method using the additional penalty term for ensuring the constraint. So following ADMM, one can develop an alternating optimization strategy as in IALS. However, this does not work well in our case. So due to the penalty term for the constraint, the update step for user factors is not parallelizable. Notice that the average user factor in the penalty term colored by purple sums up all user factors and introduce the dependency between users. We need to solve this. So for ensuring parallelizability with respect to users at the update step of user factors, we approximate the IALS objective by a linear function around the current estimate of user factors, here Z, denote the IELTS objective. So that is, in other words, that is first order Taylor expansion on the current estimate. And we here introduce the quadratic regularization term, which called the proximal term. So this may seem somewhat non-trivial approach to maintain the optimization independence, but this step magically works well for our purpose. So due to the linearization for the IELTS objective, the update step of user factors become a simple optimization problem called proximal mapping. The solution of the problem is something like this. Notice here the part colored by green is equivalent to the gradient descent for IALS with running rate gamma. So which is parallelizable, obviously. And the important thing here is that we can decompose the original non-parallel problem into the parallel and non-parallel steps, namely the gradient descent and the proximal projection. So only the remaining problem is efficient computation of the non-parallel proximal mapping part, right? So fortunately, the proximal mapping has the closed form solution due to the convexity of the penalty term. However, this leads to large computational cost, very large computational cost. First, the matrix inversion is infeasible due to the cubic complexity to the number of users, and the matrix multiplication is also costly as it takes quadratic complexity to the number of users. But we can avoid the matrix inversion by using a famous matrix identity that can have the closed form inversion for free. So no need for the infeasible matrix inversion here. There is a second challenge in the proximal mapping, large matrix multiplication. This takes the quadratic complexity to the number of users, and that's still infeasible. But closely inspecting this, you can easily notice that this multiplication can be efficiently computed. The multiplication with the identity matrix is for free, and the multiplication with the ones matrix is the identical result for each row. So we do not need to completely compute the multiplication with one's matrix by making column-wise average of the matrix on the right side, U hat, just averaging the row vectors. So as a result, we can compute the proximal projection in the linear time to the number of users. So that's a long story of our scalable optimization algorithm and item fairness. As a summary, I have the illustration of workflow of FAADMM for a single epoch in this slide. Before the parallel update step of item factors, we compute the full Gramian matrix of users and the Gramian of the auxiliary user average vector. The update step of item factor is almost the same as IALS, and the detail can be found in our paper. Then computing the Gramian matrix of items and processing the parallel part of the proximal gradient method, and then update the user factors with the final solution. The update of S is actually easy to compute by using the Gramian trick also here, and W is also easy to update. The overall cost per epoch of our FAADMM is faster than IALS actually. But this is not surprising result because we have introduced a linear approximation in the update, and thus reducing the inversion of Hessian matrix. So notably, the linear approximation will hard impede the convergence speed due to the constant running rate gamma, in contrast to the Hessian, inverse Hessian used in IALS. So I'd like to share the latest breaking news we noticed after submitting the paper to this workshop actually. To our knowledge, there is no convergence guarantee for our partially linearized ADMM for matrix factorization, but we can prove the convergence guarantee to a local optima when setting the sufficiently large penalty weight and sufficiently small running rate. This means that our proposed algorithm based on the modified ADMM can optimize the fairness of our IALS objective even with approximation in the update of user factors. So our approximation technique retains the convergence but enables a parallel computation. So I'm gonna show the experimental results quickly. So We compare FAccTRec with the state-of-the-art methods of item recommendation and confirm that it does not sacrifice the ranking quality so much on multiple real-world datasets, movie lens and the million song dataset. So we also compare FAccTRec with IARS in terms of the trade-off between ranking quality and item fairness. FAccTRec shows clearly better trade-off efficiency on both of the dataset. In particular, FAccTRec achieves almost the same quality and better fairness in the million song dataset, while it slightly deteriorates in terms of the maximum quality in the movies lens dataset. So I'll discuss the empirical efficiency of FAccTRec comparing IARS. This is a wartime per epoch when barring the dimensionality of MF. FAccTRec shows faster runtime with higher dimensionality. As mentioned before, FAccTRec is faster than IARS in terms of runtime per epoch because it omits the inversion of Hessian matrix due to the linear approximation in the U step. So this result clearly obeys the complexity analysis. So to discuss the efficiency in practice, we also need to check the convergence speed, namely the number of iterations to converge besides of runtime per epoch. Our figures shows validation measures when training IARS and FAccTRec. IARS converges quickly in about 10 epochs, but FAccTRec takes much more iterations to converge. The reason of this convergence slowdown may be because FAccTRec works like the first order optimization. So, and as a quick conclusion, this work motivated by the fact that methods in fair ranking are hard to use in large scale settings. Through the development of our method, we realized that fairness constraints intrinsically break the optimization independence and are difficult to optimize in parallel. So our proposed FAccTRec is a deployable fairness-aware method for real-world item recommendation. And also we believe that the scalability of fair recommender system is a challenging but important research direction. That's it. Thank you for your attention.
Yes, hello everyone. Hopefully you can see my screen.
Yeah, looks good.
Thank you. Yes, so today I'll present to you a paper that we wrote this year. It's called Hidden Author Bias in Book Recommendation, and it was written in the context of my PhD. I'm a first-year PhD student at CWI, the Center for Mathematics and Computer Science of the Netherlands. And my project is about responsible recommenders, specifically in the public library sector. And my project is also funded by the National Library of the Netherlands, who are interested in implementing recommender systems, but in an ethical, responsible manner, actually. So this paper was written in this context. Well, first of all, it's relevant to think in all sorts of systems, how does bias manifest and what are the sources? And as we've already discussed, maybe I shouldn't go too much into it. I think in this workshop, we all know about it, but even in collaborative filtering approaches, they don't input sensitive information, but they're still known to suffer from bias that is rather a statistical bias. And a prominent example discussed lately is popularity bias, where popular items tend to be recommended disproportionately often. But the relevant question for this work is, what about the data bias that arises from it? So if popular items tend to be recommended more often, then which items were popular in the first place? What if this initial popularity, let's say, is not random? Within the book recommendation question, you can see it as, is the author's popularity random? What if there is author bias in the initial data that also perpetuates to the recommendation process? And what if this author bias basically means that their popularity coincides with their sensitive characteristics in some way, for example, age, gender, ethnicity, etc., etc. A lot of some of these concepts have been discussed before, the gender example, but also some others are harder to contextualize in a globalized setting, which is very much what we have nowadays, the very much globalized book market. There are shifts in internet use and the way we're reading books because of the ebook market. And also there's the fact that they have this influence of large American corporations. So in this specific work, we actually zoom in author citizenship. And then the question is the author's country of citizenship relevant to the popularity bias question? So the research questions we formulated were basically, first of all, do commonly used algorithms, collaborative filtering algorithms, propagate data bias towards author country of citizenship? And also, what is the relation between this assumed author country of citizenship bias and popularity bias? And we studied this in the context of a very frequently used data set with book ratings that is commonly used in book recommender systems to evaluate different algorithms. And I will also talk about it more. As of the related work, we saw it along two axes, popularity bias and also the bias in the book market as a general domain, even outside of AI in any way. First of all, about popularity bias, well, it is known that if you just recommend only popular items to users, you can have high accuracy just because of the way accuracy works potentially, but maybe you will not satisfy other important metrics. And also lately, that's important that within the media recommender studies sector, there's been many studies on how popularity bias impacts users, and specifically how it impacts different user groups disproportionately according to whether they have affinity for popular items or more niche items. But we believe that some social connotations of this popularity bias have not been sufficiently addressed outside of this generally describing users by how much they prefer popular items. As of the bias in the book market, it's known in many studies that there's minority authors have been undervalued even in a global scale in awards. That's also known for women historically, that they've been undervalued in awards, but also publishing in general. And then you have the context of a globalized market where actually US holds the largest share in terms of sheer numbers. But other than that, since we're discussing about data sets and how do we get these data sets, and the most famous social cataloging websites where people input this information happen to be US-centric in the sense that they are American corporations, even if they are accessed by users all around the world. So overall, the US holds a strong influence in the literary world, particularly when it comes to these really renowned authors. Out of curiosity, I checked even in the Forbes catalogs, out of the 10 authors from last year that made the most money, 7 of them would be American, the other would be John Rowling and someone else. So it's, you can really see especially among the very popular and renowned ones. As of the dataset is called Book Crossing, but we also needed to further enrich it because it obviously didn't have this country of citizenship information citizenship information. So this book crossing dataset, it was scraped, I think, in 2004 from another social cataloging website that's called Book Crossing, and it's actually international. It is American, but again, in international community. The way it works is that users leave their books somewhere and then they input it in the system, and then someone can go pick up the book and then also go and rate the book and give review to the book, etc., etc. So this dataset has implicit and explicit ratings. This same dataset was used by Naga et al. For the Fairbook system that I will be referring to as Fairbook from now on, where they studied extensively the popularity bias in this dataset and in the recommendation process. So in order to compare with their own work, we also followed their own data processing steps, which basically were remove the implicit rating. So this is an explicit rating prediction system. Remove users with more than 200 ratings. So the very, very active ones that I think were around 140, if I'm not wrong, and also remove users and items with less than 5 ratings. So try to remove some of these very niche items or very not active users. We noticed we wanted to enrich this data set, but there were many mistakes and inconsistencies on the author names. For example, there would be just the name Adams, and it could refer to both Henry Adams and Douglas Adams, and they would just both be Adams because it's just how the users log the name. There's not any sort of entity recognition or anything like that. So in order to enrich it, we used other resources as well to verify the names and extract the country of citizenship for each author. And also, since we had this final verified information, we also accounted for the case where you had duplicate items with different ISBN numbers, just because, for example, it was different publications in different countries, but were actually the same book or something like that. And our entire system is available in our GitHub, and it's linked in our paper, both the data enrichment process and the recommendation process. So this is just some overview of how we enrich the data. I don't really have time to go into that, but you can definitely see it in our GitHub. But we started with the book crossing, then we used Google Books, VIAF. VIAF is an international virtual authority file where all the authors, or not all the authors, but many authors will have their VIAF IDs, and then you can link that to Wikidata. That this is the source that we actually used to extract the citizenship of its author. And here you can see what the entire dataset looked like and what the Fairbook dataset looked like. Both of them are processed in the sense that these duplicate books were removed. But anyway, what you see is that it goes from around 1 million ratings to less than 90,000 ratings. So this cutoff thresholds that were introduced by Fairbook significantly decreased the data size. As of the method, well, our goal was to measure this country of citizenship bias. So we first started by examining how the country of citizenship looked inside this data set, what was the distribution. And then we trained the same algorithms as the Fairbook system in exactly the same way as it did in an 80-20% split. And then after predicting ratings, sorting and recommending to each user 10 books, the algorithms they used were 9 collaborative filtering algorithms like 1 GNNs, some matrix factorization, neural network based, and also 2 dummy algorithms where just either the most popular book is recommended, the 10 most popular in this case, or just a random recommendation, 10 random recommendations. And finally, we compared the distribution of author country in the user profile versus in the user's recommended list for every algorithm. First, we examined the bias in data. So what you can see is that in the entire data set, so not without the Fairbook cutoffs, out of the unique books, more than 30% were written by American authors. Then around 40%, less than 40% were unknown in the sense that their information was not there in Wikidata about their country of citizenship. And then also less than 30% were something else. And I didn't put it there because I didn't want to have too much, but it could be Canada, England, Ireland, France, so Western countries, and most of them also Anglophone countries. Maybe that's significant to say. But then when the Fairbook cutoffs were introduced, the percentage of American authored books grows quite. Also, the unknown one is much less, which makes sense if you think that when you remove all the books with less than 5 ratings, then the authors are more likely to be known enough to be there on Wikidata. But yeah, also, and the other is a bit less, but the USA is really much more, which already gives an indication that since you remove niche items, that the most popular ones will be American authored books. Same goes for the unique ratings rather than the unique books, because it's also important for the system. It goes from 56% American to 74% American ratings, which was, of course, very, it was something very important for our, we couldn't ignore that. And this is why we decided to actually measure this exact thing. What is the ratio of American authored books in profile versus what it is in a recommendation? So this is how we formulate the problem, given what we found out that the data looked like. Perhaps it's important to mention that I didn't say that this book crossing community is American, but when I checked, I saw that 20% of users are American. So even if you compare to the users, the authors are overrepresented, much overrepresented. And then I have some results. I won't show for every algorithm, but you can see that, for example, here you have every dot being a user. So what's the ratio of American authored books in the profile versus in the recommendation? And you see there's a clear correlation. And yeah, this is just what's there on average in all the users' profile. And when comparing that to the work already done in the Fairbook system about popularity, you also see that user GNN was one of the algorithms for which they noticed popularity bias, in the sense that there is a correlation between the popularity of a book in the user's profile versus in the recommendation. So these are not equivalent graphs. One is about users and the other is about books, because I couldn't measure a book's Americanness, of course. So it's a bit a different perspective, but this is how they concluded that there is a popularity bias for this algorithm. On the other hand, you have this another algorithm, in this case, a probabilistic matrix factorization algorithm, and you see that there's no any correlation, actually almost nothing between between the ratio in profile of American author books or in recommendation for a user, and even you have on average less American authored books recommended than a user's profile. For the same algorithm, also the Fairbook system didn't find a popularity bias, which goes along with the idea that this consistency bias is a result of popularity bias. I won't go through its algorithms, but I have an average result. So here you can see on average every algorithm, how many American authored books recommends, and how many, this red line is how many are on average in their user's profile. So you can see that some algorithms, including the dummy most popular one, increase this ratio, so they recommend more than on average in the user's profile. And the same algorithms are the ones that, according to the popularity bias work, during the Fairbook work, on average increase the popularity. So this delta gap metric, I'm not going to go into it too much, but it's a propagation of popularity bias metric suggested by Abdollahpouri and al. In the original and fairness of popularity bias work. And basically what you can see, sort of in the same way, the algorithms who propagate popularity bias are also the same, that increase the number of users and the number of American authored books in recommendation versus in profile, even though there's not the exact same manifestation in an average sense. But if you feel free to read the paper and look at all the algorithms separately. So to answer the research questions, first, we say that yes, certain algorithms do perpetuate data bias towards author country of citizenship. Specifically, American authors were favored by some algorithms by being disproportionately recommended. And second, there is definitely a clear relation between this popularity bias in this author country of citizenship bias. I realize now I forgot to mention that also among the popular book, there was significant relationship between book popularity and the author kind of citizenship of this book. So already from the data, we knew that If I had to choose two main takeaways of this, is that first of all, popularity bias is not just a random phenomenon that can be, it's not just a statistical problem or a performance problem, but it's also a problem when an organization uses a recommender system that wishes to account for this bias, as is the example for the library that I mentioned that my project is funded by, but also generally for other organizations who care about this. So popularity overall is not always a bad criterion. There's some interesting work on how popularity bias is not always a bad thing, but we should be extremely careful when it coincides with certain item properties that, because of historical context, they happen to coincide, and not just because objectively these books happen to be better in some way or another, just because they're the most popular. At the same time, it's definitely noticeable how this is another example of lack of geodiversity in linked open data. And yeah, it is a known problem, and it definitely requires solution, especially if you think that this data set was used by many teams around the world to evaluate all sorts of algorithms. So as of the next steps, well, first of all, as it was mentioned, I think also about a keynote speaker, but generally by other teams as well, this was an unsought recommendation, and it would be very, very useful to use feedback loops to simulate how would this phenomenon progress throughout multiple iterations of recommendation and assumed consumption or some other strategy. Also, we really want to verify and expand this data enrichment process, because we think that a data set like that that's complete with this information can be useful for the community to study bias in a ratings data set. And we plan to use crowdsourcing for this exact purpose. And finally, we want to center this bias question and how it surfaces in book recommendation, because this is a key topic for us. And so we would want to also approach it from the perspective of users, but even more generally, in an abstract way, the book themes. How are the book themes treated by a system? So yeah, that's it. Thank you very much.
I'll pick this up so I'm not stuck behind the podium. That I don't like being stuck. So I'm going to talk to you today about this concept of matching between objectives and strategies or solutions or intervention points and ideas in solving problems of consumer fairness recommender systems. And this is a position paper that I co-wrote with Soleil Pera, who has been doing work for many years on recommendations and information retrieval for children. And so in this, we kind of weave together these two ideas of consumer fairness as we've been studying it in the fair recommendation and fair IR community, and ideas of designing recommendation systems, information retrieval systems, et cetera, to meet the needs of particular user groups that are not often well served by technology that's built for a default user, typically a younger adult person. And so in fairness, as we know in this workshop, fairness is, in general, is a complex problem. And in recommender systems, it's a complex problem and it's a multi-sided problem, because we have consumers, we have providers or producers, we have various other potential stakeholders as well, such as subjects of news articles and things like that. So in this work, we're particularly concerned with being fair to the consumers in some way. And when we're trying to do this, we have a lot of there's a lot of subtlety here, because the system's trying to personalize to different users. The system's trying to meet each particular user's needs and preferences and tastes, finding items that are going to be particularly appealing to them. And we're trying to do that in a way that we can assess whether or not is fair, which requires us to be able to compare these very personalized and particular experiences across very different users. So it's not an easy problem. But the basic idea of consumer fairness, just to rehearse and set the stage a little bit here, is that we want to ensure that the system's users or the consumers of its content are being treated fairly in both the quantitative For example, the accuracy metrics, the amount of content that's available to them, things like that, and the qualitative aspects of their experience, what that actual content is, how it relates to their needs, to their interests, etc. And we can think about doing this both individually. Each user should receive good service from our system. We see this showing up in a variety of things such as user cold start and the work on like disaggregating averaging metrics by users. So we like weight each user active equally rather than overweighting the users that are more active in the system. And we can also look at it in groups, making sure that users of particular genders or particular ethnicities or particular ages, say teenagers, are getting comparable service from the system and are having a fair experience with it in some way. So our key point in this work is that there are many different ways that we can intervene to try to provide this kind of fairness in the system. And we need to select the intervention strategy that advances specific fairness goals in the specific context of the particular recommendation problem we're trying to solve, the particular application we're trying to solve it in. And there's no just one size fits all, oh, here's how you do consumer fairness. Because each of these problems, each of these applications has its own particular needs and calls for a different solution. So if you get this, you get the central message, hey, you need to actually match those, you have the whole point. But what are some of the things this actually looks like? So I'm going to start by talking about a few objectives that show up in some of the consumer fairness and related literature. One is what we're calling equity of usability. And what this means is that different people are able to actually use the system. If you have a system, maybe over in a search side, which requires a fair degree of fluency in order to type in a query, then it's going to be harder for children who are just learning to express themselves in written language to use the system. It's going to be harder for, if it's in English, it's going to be harder for English as a second language speakers who don't have the same level of fluency in written English to use the system effectively. If it's a recommendation system that presents a whole lot of confusing information for, it's going to be harder for people who don't have the level of expertise to understand it to use it effectively. And so we can look at trying to make systems that are usable by everybody, or at least usable by everybody in the set of users that we're going to consider. The next one, and this is probably the single most commonly studied consumer fairness problem, is equity of utility. And equity of utility is looking at, we want different users to get the same quality of service. So your recommendations should be just as good as your neighbor's recommendations. The recommendations that women receive on the platform shouldn't be worse in terms of meeting their needs, meeting their interests than the recommendations that men receive on the platform. And the recommendations that non-binary users receive on the platform shouldn't be worse than either of those groups. And so we want to make sure that different users get these kinds of comparably useful results. And at the individual level, this is where that averaging thing I talked about came in, where like if you look at the performance on a user by user basis, and then average that across users, then each user has equal weight in your final system performance. If you say compute it on a session by session basis and average across sessions, then the users with many sessions are going to be weighted more highly in your overall performance metrics. So that's one way it works out individually. Group-wise, you can disaggregate and look at things by the different groups of users and thinking about what their utility is and setting this objective. Another one is fair representation. So we want to make sure that users, I mean, we think about representational harm somewhat a little more easily in provider-side fairness. We want to make sure that the item and its provider is fairly represented. But users can also have this concern of the system, both internally in its representation, say it's user embedding that it learns for you, but also then in how it represents you back to yourself, or if there are social features, how it represents you to other users on the platform. We want to make sure that's fair, and that for a variety of things, we want to make sure that there aren't, in many cases, that there aren't stereotypical aspects to your representation. You want to make sure that the representation, say, is not associated with bigoted terms or images in how the system is being, how the user is being represented. So, and then these are not an exhaustive list. We could think of many, many more types of objectives that we can see, such as this morning we heard about avoiding harms, particularly mental health related harms. So we can look at wanting to avoid harms in general, but also particularly attending to harms that might disproportionately affect already vulnerable users on our platform as a fairness matter as well. So there's many, many different things we can try to achieve. Now, to achieve these, there are a whole bunch of different interventions that appear at different points in the overall life cycle and in the technical structure of the recommendation application. And the first one we want to talk about is design. And this one, I mean, it can particularly match for some equity of usability things, but we can think about when we're designing the system, both designing its user experience and also the design process for its algorithmic components, for its data processing pipelines. We can pay attention here in how we're doing the design to whose needs are we prioritizing? Are we designing a system that's going to be usable by a range of people? Are we, maybe in some cases, we might need to design different systems or different front ends to the same system to meet the needs of different users. Like we might want to have an interface for children that maybe it does some algorithmic changes, but it has a simplified interface. Maybe it has more support for helping them find things. Maybe it has more visual representations instead of orienting search for help them figure out what music they want to listen to. But we can look at the design aspect of it in order to either make the design more useful for more people or differentiate the design to meet the needs of different groups of users who might be using our system. We can also look at the algorithms themselves. There are many proposed things in the literature that modify the algorithm in some way to improve many different fairness objectives. And you can see the paper for citations. In this 2-page paper, we have 59 citations. So there's lots of related work to go read. And the algorithm details, I'll leave that for you to go read about, but most of us in here have read some papers that have different algorithmic suggestions. We can look at the data. We can look at trying to improve the data that we have to support better meeting people's needs. Sometimes this can look like collecting more data, but sometimes it can look like collecting better data or doing better inferences over the data that we are collecting. Paying attention to things like, okay, the way that the implicit feedback signals that we get to understand, did the user like this recommendation? Well, are we correctly interpreting those signals across different groups of users? Or do some users respond in a way that has a different matching between their responses to the system and their actual satisfaction? Can we account for that in how we in how we're doing our data processing that feeds into the actual algorithms of the system? Are we making sure that we have comparable quality, say, of product metadata for products that are going to appeal to a wide range of our users? Or do some users' interests have very good product metadata and other users' interests we don't have as good a data, and so the system's not able to compute as good a recommendations for them? Lots of things we can think about in the data in order to work to see that as an intervention point for working on consumer fairness. Another one is in the process, and by this I mean the engineering process of how it is that we're building and maintaining and understanding the system. Not everything is necessarily directly a technical intervention. So if you say have audited that you have different utility between different subsets of your user base, and you further identified why, it turns out that, I'll use the children example again, your system's not able to do very good matching between children's preferences and the songs that they might like listening to. Then we'll assume for a moment that maybe you're using something like Scrum. And so in your next sprint planning meeting, you can, if you've got a couple of features, one of which is going to make the system better for users who are already having a good experience, and another one is going to make the system better for users who are not having a very good experience, you can prioritize the one that's going to help the users who aren't getting very good experience with the system. And just that prioritization in the engineering process, that can be a fairness intervention. It's not one that we talk about very often here. One of our calls here is, let's think about this. Let's think about where all in the pipeline we can actually intervene to make our system work better for all of its users. We can also look at marketplace interventions. If someone's system is not providing a very good service for some of its users, you can go compete with them. And you can provide a good service for those users. Or if you notice that your service is not providing very good service for some of your users, you can either maybe spin up another product. Like it might be a case where it doesn't make sense to try to make one product that works for everybody, but you can spin up another product or a version of your product that's going to meet those needs. We don't necessarily have to, the goal isn't necessarily to make every individual product work for everybody. The goal is to make sure that everybody has good and effective access to recommendation. Sometimes that's going to be one product. Sometimes that's going to be with a suite of products and helping users find the one that's better going to meet their needs. So with all of this, we have a number of different objectives. We have a number of different strategies. Again, the strategy list is probably not exhaustive. I would love to see work on a plethora of strategies. The key thing we need to do is match, identify what strategy, what intervention point, where in the system are we going to intervene, how are we going to intervene to improve fairness, is actually going to advance our particular goal and address our problem. And again, this depends on our application, domain, users, etc. So a couple of examples. So there's one paper, I don't have the link to it up here, but we cite it in the paper, by Alex Butel et al. At FATML 2017, that was looking at the issue of bias and representational bias in user embeddings in the system. And so they wanted to make sure that the user embeddings aren't encoding the user sensitive attributes and therefore may be prone to reproduce stereotypes. So what they did was they adopted adversarial learning, and they stuck a discriminator in there that attempted to predict the user's sensitive attribute from their user embedding. And then they ran the adversarial learning algorithm to optimize good recommendations with user embeddings that are not predictive of, say, gender. And that kind of a design is a good match because it's taking the problem. We don't want to encode this attribute and reproduce as a mechanism by which we might reproduce stereotypes, and designing an invention that's directly targeting it. We can also look, so if we want to look at comparable quality of service, as I talked about, we can prioritize engineering features. That's one way we can do it. Another way, we can target, we can adopt a zero or a positive sum objective function that looks at different groups. For example, say the sum of the logs of the group utilities, so that you need to bring up the groups that don't have as much utility. You want to be careful though, because if you say, look at just the differences of utility, that's a zero-sum game, but utility isn't a rival risk good. My good recommendations aren't the reason you're getting bad recommendations. So identifying and targeting the match to actually engage with what the nature of the fairness problem really is. Rivalry or subtractability is one of those things. So the goal with all of this is to provide a good match between the strategy and the objective so that we can provide effective service to the users in all of its different ways, quantitative, qualitative, all of the different ways that that users experience the system. And so that's our point. Our point is to start a conversation or advance the conversation and highlight the need to pay attention to the particularities and to have a good match between strategies and objectives for good recommendation. Thank you.
Okay, hello everyone. I just need to close the chat here. So, okay, yeah, thank you for this great talk. And we're now talking a little bit about the role of bias in news recommendation during the COVID-19 pandemic. My name is Thomas Kolb. I'm a PhD student. I started my PhD this year, and I'm working together with Irina Nalis, Mete Sertka, and Julia Neidhardt, because two of them are here in the audience. And we are in a new lab at TU Vienna for doing news recommendation. And therefore, yeah, we presented here our research. So let me just check how I can go further. Okay. Yeah, before we start, this is the agenda for today. We will see a little bit about the problem statement here. Then what's currently done in the research, because we do have interdisciplinary research. We have a psychologist in our team. And you will see that we have some like relations to the topic here. Then the contributions about which data we use here. And then we have two different aspects. First, we had a descriptive view on the data set which we use. And secondly, also at the change in user behavior and the potential impact on our recommender system. And last but not least, we will just have a short discussion and a future outlook. Well, yeah, before we start, we have always like recommender systems can be used and also abused. And therefore, it's important to have a responsible news recommender system. In this case, a news recommender system, but I think this also applies for different domains. And our goal is here to show that one needs to take care if the data changes or so to have a responsible recommender system. And this is also be shown to have a depolarizing capacities once they go beyond accuracy measurements. And this is also one of the main goals in our research project. For a problem statement, we see here as we researched that often many publications are done with small data sets. There is often a small, short time span used for evaluating some phenomena, and also often the temporal effects over time are not investigated in depth. And this leads us to our goal. We are especially interested in the impact of changed user behavior on recommender systems in this case. Yeah, therefore we will have a short outlook into a case study, which shows that looks at the COVID-19 pandemic, especially on online news content and user behavior. And I will just introduce now some terms here, which we have. This is also coming a little bit out of the psychology area. There is this term, and there is shown that there is a certain relation of bias in agenda setting. At agenda setting, in this case means that states or countries are like outlying a certain agenda to news corporations, which then behave in a certain way. And this introduces also bias in news reporting and news coverage for certain topics. The second thing is the term rally around the flag, which means in this case that if something happens like the Corona crisis, the users are flocking around this topic quite heavily, but then it also is also shown that this declines over time and they lose interest. Like we also see that in the data that in the third Corona wave, the interest of users already declined. And the next one is there are several papers already out there which investigate this change in user behavior, not user behavior, but which wrote about how this pandemic affected news reporting. And they're especially about fake news. And they showed also that there is a certain polarization in discourse in place. And yeah, last but not least, the term news burst just means that there is a high increase in news coverage and also in coverage of this specific topic about the pandemic taking place. And yeah, this all can be a potential reason why a recommender system is going into some kind of potential filter bubble. And this needs, of course, to be explored. Yeah, before we go into depth of the methodology, we will just show shortly the contributions. In the first part, we will show that there is, in fact, based on our data, an increase of coverage of the COVID-19 topic. And there is also change in the news reporting itself, that there is an increase of corona-related reporting in Austria, in our suspected area. And secondly, we will show that there is a relevant flag effect visible, that there's a strong increase in traffic also on the user side, not only on the news media side, and that this leads to a decrease of topic diversity, and also the recommender system has a less high topic diversity in his predictions. And there is, of course, in the last line, a risk of incorporating a certain bias into recommender system. Well, we now heard a lot. The data which we are using are from the biggest online community in Austria. This is a daily newspaper called The Standard. We use a large real-world anonymized data set, and we do have articles and also some kind of keywords which relates to what this article is about. For example, if it's an article about corona, then we know that this corona article is related to that topic. We also do have the user behavior, for example, user postings, clickstreams, and other metadata from the last 20 years. But for this research, we look at 4 different time spans: the pre-corona time, where we took half a year of data, and also the different waves, which is already about the same time span, around 6 months. Well, then to the first part, we do have here 2 questions which we want to answer or show what we got out. There is this pandemic which affects the content of how does this epidemic affect the content of a news outlet, and also how does this affect the reader's commenting behavior. And we can, how did we do that? We saw that we analyzed the article topics and then their assigned keywords, and also had a look at the frequency of the news articles, and also how there was a change in user commenting behavior of the users. And for example, here we can see this is now due to it's a German, like an Austrian news outlet, but in German terms. But the first one is car for auto, and we can see that pre-corona there was like this car, which is very let's say everywhere, like because it comes a little bit from Germany, because they have a lot of stuff ongoing with cars. This was the top keyword here. And one can see that in the first wave, for example, coronavirus was already above. This was the first wave. And then in the next wave, for example, all of the top keywords are related to some corona-related articles. That means that the count of articles was related to coronavirus. And also in the third wave, but here we can see that car is coming up again. And this also shows a bit this really around the flag effect, where the interest also in the news outlet declines over time. We can see that also in the graphic below. This is just aggregated articles per month. And there we can see that on 2020, April, there was a strong increase in corona-related articles, where nearly half of all articles which this company published were related to some corona topics. To the second question, how this, now we saw like the news outlet perspective, and this is now the user perspective, how their commenting behavior was, because they're able to comment below each of the articles. And there one can see also the same effect. Here is, it's 2020, April, we can see that nearly all postings were to some corona-related articles, which is quite interesting. And we can also see that there is this mirrors the interplay between media coverage and behavior to stressful events. We can also see this same effect, that interest also declined a little bit later, and this is the same behavior as we also saw from the news outlet itself. Okay, then to the second part, and this is now more related to the recommender systems area. We just saw it descriptive, and now we will have a look at to what extent these disparities in data set are reflected on the recommendation performance. And therefore we use the sequence prediction model, which we will see very soon. And the fourth question is also how this affected the topic diversity of the trained models. Like if the predictions are less diverse, for example. And there we can see, before we go to the approach, we see that we use BERT for Rec, which is quite it's not, yeah, it's one of the state-of-the-art algorithms for sequence prediction, where we created just, as usual, a train and evaluation data set, whereby our relevant metric was the mean reciprocal rank of the last top 10 items, whereby yearly stopping was applied during evaluation with the validation data set. For the metrics, we used in this case only 1 week intervals for each of the different waves, due to we had like a very high amount of click data. I think in this table are like more than 700 million rows. And this was like a good deal for us to have it like in time ready and to get some good results out of it. For the recommendation similarity metric to show the topic diversity, we used a pairwise Jaccard similarity of the top 10 recommended articles for each session, whereby one session is if a user goes to the website, clicks a certain amount of pages, and this is counted as one session. And this was then aggregated and averaged for each interval. And yeah, and the goal for the sequence prediction was to predict the next to be clicked news article in this case. Well, we can see here that there is a traffic increase in the amount of sessions, and that yeah, nearly all metrics, like if you look at the sessions, you can see that it raised a lot during the first and second wave. And that's also, for example, the amount of articles was high, around 50K, which then decreased during the first wave, and then went to the same high level as before, which was also reflected here a little bit through the average actions by article from a user. But we can also see that it stayed on a high level on the second wave, which is quite interesting here. For the total clicks here, we can also see a very high increase in clicks in general on the news outlet, which indicates that the users are really using that kind of news platform more than before. And this also stayed on the high level, as we can see later in the second and third wave. For the metrics, we can see that we first had an MRR of 0.17, which then went higher, but this also makes sense in this case due to we had like a concentration around the lesser amount of articles, but it also stayed high in the end, which could be also indicate that there's some certain of kind of filter bubble or like bias in place now in the system. Okay, and now the interesting one is the Jaccard similarity. And here we can see really that's just to explain, a 0 would mean dissimilarity, and 1 would mean complete similarity of the compared articles. And we can see here that's the that the topic diversity was worse. Let's say like this. There were more similar articles recommended, and therefore also this metric is higher, but this lowers the diversity. And this is no good thing if we see no good thing if we see that that we want to have like a recommender system which has diverse results, which we can see here. Yes. So as a short summary, we had this now. I mean, some of the terms are already known now. We had this concept of media biases, which we already showed before. We also saw that there was a certain burst around this event. And we saw that there is a rally around the flag happening. And there is a potential filter bubble there by these other effects. And just for the discussion now, this also leads to the result that one needs to go beyond accuracy, and that it's not enough to only look at accuracy itself, and which we can also see here through the keyword crisis and this event burst. And that there is also a lot to do in the future. For example, one can also look at the commenting behavior of users. If there, for example, is a change in sentiment there, or one can do network analysis, or also looking at the emotions of users, which like how they write and how this changed over time in these stressful situations. Yeah, and we also see that this is now based on a sequence prediction, that there are some problems with it, and one needs to mitigate that, which we can see here to counter developments of a decline in diversity, and also that polarization took place here. Well, I'm already on my last slide. We showed that this temporal dynamics of topics during the COVID time were here, and also that this changed the user behavior on recommender systems, and that there is future work possible in a lot of ways. Also, for example, to try out recommender systems of different recommendation families, to just compare it on a broader range of different algorithms, and to also investigate a longer time span, which would be also interesting to get more long-term data. And yeah, as I said, one could also include posting data, for example. Yeah, we are happy to get in touch with everyone. This laboratory started this year and will be here for several years. And this is one of our main research areas here, and we will try to deepen everything in the future. Thank you very much.
All right, welcome everybody. I am Carlijn Dinnissen from Utrecht University. And today I'll be presenting work I did together with Christina Bauer, who's over there. And the topic is a stakeholder-centered view on fairness in music recommender systems. And the structure of my talk is as follows. I guess I'll click like this. Okay, the structure of my talk is as follows. First, I'll be giving you highlights from a narrative literature review that we did and published in a previous paper. And then I really want to focus on the challenges that we identified when we were doing this literature review. And hopefully we can get a bit of a discussion going, and we can get some input from different fields, people from different domains, to see how we can tackle those challenges. So first, the research question that we had for our literature review was, what is the state of the art of music recommender system fairness research from the various stakeholder perspectives? So we were looking at each stakeholder and identifying fairness research for them. And this, in very short, is the results. In music recommender systems, we saw three main stakeholders in literature. First of them being the platforms offering music streaming services. You can see a couple over here. And then secondly, there are, of course, the users that use these systems to access and listen to music. And thirdly, there is the artists, the providers of the items, providers of the music of these systems, and also labels associated with artists. And then what makes this an interesting field for fairness research actually is, well, first of all, like Michael Ekstrand just explained, for users, there's equity of utility. Every user, regardless of where they're from or what their characteristics are, deserves a good experience listening to music, because music has a very important part in people's lives. And then for artists, these are numbers from last year, but streaming comprises about 65% of the total global music industry revenue. So that's really a lot of money. And that means that if artists are being treated unfairly in the system, that means that they don't get the income that they might deserve. And that's something we really should aim to prevent. And then, of course, these stakeholders don't exist in a vacuum. They are together in the system. So that's why this is a multi-stakeholder system. And we should aim to make the system fair for each stakeholder at the same time. And now on to some statistics. We identified 24 papers in total that were specifically about recommender system fairness in the music domain. And more than half of them were from the user perspective, so considered user fairness. There were 6 considering fairness from the item provider perspective, so the artists, and there were 5 looking at multi-stakeholder fairness. So that's a couple papers, but still we've got a lot to do there. And then zooming in a little bit on what is then actually looked at fairness-wise, we saw that both for the user and for the item providers, mostly group fairness was considered. And then these groups, they had quite a lot in common for the 2 stakeholder groups, like considered attributes like age, country, gender, where people are from, Those were existing in literature for both stakeholders. And there were also some more stakeholder-specific attributes, like mainstreaminess for users, the extent to which their taste is considered to be mainstream or not. And then for artists, of course, there's popularity, but also how contemporary an artist is, and also the artist type, like is it a group or a solo act. And some of the literature also doesn't focus on one attribute at the same time, but considers a lot of them. And now on to the challenges that we identified. And the first main one being data set availability. So out of the papers that we reviewed, there were 4 that didn't use any data. But from the ones that did use data, more than half of them were using data that originated from Last.fm. There's different variations, but we know that Last.fm, the user base, contains mostly Western users, also mostly white male users, and that makes it difficult to be sure that we can say something about fairness in the real world for all users that use music recommender systems. So yeah, that's definitely something we should keep in mind. And then also 1/4 of the papers used proprietary data sets, so sets that are not available to researchers outside of the organization where the research was done. And therefore we also cannot use that. So definitely we should try to get a broader set of data that we can use for evaluating and improving fairness. And regarding that, there's the second challenge. We divided the papers that we saw up into papers that were analyzing or evaluating the current situation in the system, considering fairness, and papers that were aiming to improve fairness in recommendation systems. And we saw that at the moment, most are focused on analyzing the situation. And while that is super important, because if we don't know what's happening, we also don't know what to improve, we should really aim to also then actually improve the situation in music recommender systems so that we can make sure that we actually make the systems more fair. And the one exception you can see are the multi-stakeholder categories. There are more improving fairness aimed papers. And that's likely because it's a multi-optimization problem, which automatically then implies improvements. Okay, so brief recap of the challenges, and we're super open to any comments or ideas about this. And then a couple of specificities that might make it difficult to adapt fairness measures or methods to improve fairness from other domains into the music domain. There's a couple characteristics that make the items quite special. Like if a user is looking for 90s music, there might be a lot of items that actually would satisfy the user. So there's often not one best item that should be returned. Then a lot of users listen to music on repeat, maybe a lot of times. Also, music has a long lifetime. We're still listening to music from the Beatles. We're not still reading news articles from the 60s most of the time. And items are shorter than movies, shorter than books, shorter than podcasts, also makes it a difficult thing. And evaluation-wise, we don't have a lot of explicit rating data, and implicit data like whether a song is played doesn't necessarily mean that a user liked the song actually. And lastly, the real world also contains biases, like currently about 75% of the artists are male. So there's already a skewedness, and yeah, it's important to think about how we should treat fairness in those cases. And thereby I come to my last slide. Yeah, contact us please if you have any input. You can see the paper and the full overview through the QR code there. And thank you for listening.
Okay, hi everyone. I'm Amanda. It's my first year in my PhD program at the University of Colorado Boulder. And today I will be presenting the position paper, Who Pays, Personalization, Bossiness, and the Cost of Fairness by Patricia Ferrestu, Nicholas Mate, and Robin Burke. So in this paper, what we're going to be looking at is the question of consumer-side unfairness arising as a consequence of provider-side fairness constraints. So a key concept in this paper is going to be looking at the cost of fairness, where we're concerned about the idea of users receiving lower utility than they would in a system that is unconstrained by fairness objectives, in the sense of provider-side fairness objectives being put into place. And we want to look at what the distribution of this cost is going to look like. So this graphic is going to be something that I'll be referring to through the slides when we're looking at where a user lies on the spectrum of what their individual cost of fairness is going to be when fairness is personalized. And then the next key concept that we'll be using in this paper is the idea of bossiness. It's a concept that comes from social choice, and it's the idea that users can manipulate their input in a way that harms others without getting worse outcomes for themselves. So an example of where this would happen would be like in ranked choice voting, where if you know that your first choice that you want to vote for isn't going to win, but your second choice has a good chance, you might put your second choice first over what would truly be your first pick. And we will be applying this to the recommendation concept. So here, the user's input is going to be their personal user profile. And we extend this concept into the idea of epsilon bossiness, because the original concept of bossiness doesn't quite cover everything that we want to get across. So we want to look at if it is worthwhile to be bossy if you are going to be reducing the cost of fairness while also losing some accuracy that the model is gonna, some of the model accuracy. So in a situation where the loss of model accuracy is going to be less than the cost of fairness and ultimately increasing the user's personal utility, making it worthwhile to be bossy. So quickly to go over kind of the application of this, we want to be considering the idea of epsilon bossiness in the long-term aggregate fairness context. A quick example would be on the platform Kiva. It's a micro-lending platform that connects borrowers and lenders. Say there's certain countries that that we're protecting in the provider-side fairness application. If a user were to avoid looking at a specific protected country because they know that looking at that will cause them to get more recommendations from that country. That would be kind of an example of this. They're ultimately not looking at a loan that they might want to fund. However, in the end, it's still going to benefit them because they're going to get less recommendations from those countries. And if you want more details on the application that we're considering to look at, you can refer to that paper down there. So finally, we're looking at some of the approaches to how to deal with epsilon bossiness. The first approach we consider is just dropping the personalized approach to fairness overall. This will ultimately result in lower accuracy and utility for users. But we would see here that all of the users would be taking up the same cost of fairness because there is no personalization. But it loses the benefit of a personalized approach to fairness, particularly it's a problem for multiple fairness dimensions when we're looking at users as opportunities to pursue different aspects of fairness. The next approach that we consider in the paper is implementing a minimum fairness requirement. So users will be required to at least bear some cost of fairness. Each user will be, and this would mean that users don't gain as much from a bossy strategy. So they're starting from the end, and there's not that far that they can go in changing their cost of fairness. And the third approach that's looked at in this paper is implementing a maximum cost of fairness. Similar, but also the opposite of the last approach I talked about. This would prevent any user from taking on too much of the cost. So with no user having too much of the cost, there's less incentive for a user to be bossy. And the burden can't be shifted too much because of that upper bound put into place. So what this position paper is proposing to look at is studying the system vulnerabilities to bossy strategies and possible responses. So for an example, the second two strategies are the strategies that we want to focus on. And in the Kiva context, with the microlending platform connecting borrowers and lenders, it's an interesting question of looking at which approach would be more effective. Would we want to look at it more from implementing this minimum cost of fairness that all users are going to have to take on? Or could it be more effective to implement this maximum cost of fairness so no user will be carrying too much of the burden? And lastly, a question that we want to consider is there a possibility that we can persuade users not to be bossy? And thank you. If you have any questions, please feel free to email me and I can connect you with the authors for the paper.
Hi, everyone. So yeah, I'm here to talk to you about our paper. Can I take this off? Ooh, that's way better. Okay, I'm here to talk to you about our paper, What Are Filter Bubbles Really? A review of the conceptual and empirical work that I co-wrote with all of the bubbly people on this slide. It was originally presented at the Fair UMAP workshop earlier this year. If you were there, I changed my slide completely, so don't worry. So yeah, but in the interest of time, and since I'm the last presenter of this session, I decided to do something different. And not walk you through the paper, but instead try to focus on why we wrote this paper and why we think it's important. And then hopefully I'll be able to convince you to go and read it. And if you do, what you'll find in the paper is an overview of both the conceptual work on filter bubbles, so how people try to define it in media studies, in philosophical literature, and also how has it been approached in the empirical work, so more on our end of things. And then a bit of a discussion of the roadblocks to success in filter bubble research, or the way we see them, and how we could overcome them. All right, so filter bubbles, clearly talked about a lot, keeping a lot of people up at night. I also work in industry with news companies, and it's one of the first things they always mention, like, oh, personalization, aren't we going to be creating filter bubbles? And so in that sense, it's really great that there's also been a lot of academic work on the subject of filter bubbles. When I made this slide back in June, there were about 7,000 citations of Preiser's book, in which he coined the term the filter bubble about 10 years ago or so. And I would bet you good money that at least 100 of them propose the technique to combat filter bubbles. I haven't gone through all of them, but I'm pretty confident it's at least that many. And so if any one of you wants to hazard a guess how many of those 7,000 citations are empirical studies of filter bubbles, like audit studies, controlled studies, observational studies, in which they try to find filter bubbles and understand them, it's 12. Out of all of those, it's 12 studies. And so, you know what, I thought, let's talk about them, those 12 studies. So let's start with the good news. All of them agree that filter bubbles are about diversity, which is great. But that then it gets tricky, because then it turns out that 83% still agree that it should have something to do with recommendations, and the other 17% seem to think it's something else entirely. Even though in the original sort of definition that you can find in the book, I highlighted this word internet filters because personalization apparently wasn't really a big term back then, but I'm guessing personalization is what he was referring to. So yeah, and then it gets even worse if you start thinking about the dimension of time. Turns out that 33% of works treated as a sort of longitudinal effect. So there's a component of time, some amplification of seeing more and more things that are tailored to you over time. And then another 33% thinks it's about like differences between different groups of users, some more like fairness type of thing. And then 17% studies it as differences between different algorithms. Even though, again, referring to this original sort of definition, he refers to it as something that is so that internet filters are constantly creating and refining a theory of who you are. And then a later definition, the conceptual work, clearly just states, okay, they're created over time. So I think it should be clear from this that this whole field of filter bubble research has been plagued with a lot of ambiguity. There's a bunch of interpretations out there of what it is, like what a filter bubble is. And most of them in the empirical literature, at least, are quite like implicit. You'd have to read the experimental design and everything to understand how they set up the experiment. There's also a lot of negativity associated with it. Lots of people in our field, at least, don't like talking about them because it's the first thing we're always confronted with. Oh, you do recommender systems and personalization. Great. So what about filter bubbles? No one likes that. And then now it appears like there's even like in recent years a bit of a fatigue with a bunch of influential authors on the subject writing papers that say that it's, we shouldn't be talking about filter bubbles anymore. We should just ignore the term. I disagree. So we thought, haha, maybe it's just because there's no good definition. And then this XQCD always comes to mind with the 15 standards or the 14 competing standards. And then we thought, you know what, we'll add one more. I'll let you decide if we were successful or not. So we tried to come up with an operationalized definition of the technological filter bubble, and we defined it as a decrease in the diversity of a user's recommendations over time in any dimension of diversity resulting from the choices made by different recommendation stakeholders. In my understanding, there's 4 key components to the filter bubble. There's the dimension of diversity, there's recommendations, there's a component of time, and then the last one that we added because we thought it was important was the recommendation stakeholders part. Because of course, you don't just want to know that a filter bubble exists on a platform, you don't want to know why it does. Is it because users consume like very niche bubbly content, let's say, or is it because on the provider side, there's just not a lot of diversity available, or is it because the system owners are like prioritizing the wrong decisions, like relating back to Michael's talk. All right, so key takeaways here. Even if I wasn't able to convince you of our definition, I do hope I was able to convince you that we should keep studying filter bubbles because it's important and people talk about it. And that at least we should try to define what we mean when we use the term filter bubble. And then maybe if I can hope a little bit, use our definition. All right, that's it for my presentation. Are there any questions?
Cool. So hi, my name is Rebecca. I'm affiliated with the Université de Montréal, UDEM Mila, and my collaborators, Fernando Diaz and Gulnush Farnadi, are also affiliated with Google and HSE. And today I'll be talking about analyzing the effects of sampling in graph neural networks on individual fairness. And so the way that this talk will go is I will present, the general motivation, lay out the scope of our specific contribution, provide some background on graph neural networks and individual fairness, and then we'll dive in. So the premise of this work is that we take an individual fairness framework called redress, and we apply it to our setting. So I will give all the details about this individual fairness framework, and then I will go through our results, present our conclusions, and then maybe, if we have time, lay out some directions for further work. So, at its core, graph neural networks have kind of permeated the space of recommender systems. It's without a doubt in the last few years, one of the few very prominent architectures in this space. And this is done because, graph neural networks are specifically suited to kind of learning representations that are not just individual, but also community level. However, this iterative process of representation learning has also kind of issues that are endemic to graph neural networks that can lead to biased representations. And this is particularly important for our setting because, biased representations that are used in recommendations lead to biased recommendations. So this is a problem that we need to mitigate. So the main thrust of this work is to take an individual fairness framework called redress that was developed specifically for graph neural networks. But one of the, the technical contribution of this work is that when it was originally proposed, the redress framework was limited in the graph neural network that it selected, and it was not compatible with large graphs. And as we all know, the orders of magnitude that social networks have. So this is a problem. This is the, the technical issue that we need to overcome if we want to promote individual fairness in the graph neural network space using this framework. And so what we do is we take this individual fairness framework and we extend it to a scalable method called GraphSage. And when we compare the performance and we see, is it still feasible to use this form of, fairness promotion? And what we do find in our implementation is that yes, mini batch training actually achieves better performance than training on the whole graph as was originally proposed. And in doing so, we kind of uncover this relationship between individual fairness and the neighborhood selection that's being done by the scalable method. So now I will just, give some brief introduction to some of the methods that we use in our paper, but if you want more details, you should read the paper. So graph neural networks and recommender systems kind of go hand in hand very intuitively because humans are social creatures. So if we want to figure out, whether you're going to buy an iPhone, we don't need to just look at your bank account. We can also ask your friends if they have iPhones, and that's actually really predictive. And so now we want to have this kind of way to define your network, and we do that through a graph. And we want to define the scope of influence on you. And so the kind of breakthrough in this field came from taking the idea of convolutions from images and putting them into the graph space. And this bred graph convolutional networks, which is the initial method that was proposed with the redress framework. And at their core, the way that graph neural networks work is they have these two functions, aggregate and update. So aggregate collects information from your neighborhood, and then the update function integrates the information of your friends into the representation of you or the representation of an individual node. And so graph convolutional networks, they collect an entire neighborhood, everyone you've ever talked to, and they train over an entire graph. However, this is intractable. So if we think about putting a massive graph on GPU, this is just not feasible. So what GraphSage does is it takes the training regime that's using graph convolutional networks, but it modifies it for mini batch sampling. So it samples P neighbors. So it's not using all of your friends, just some of them. And then it also does so in mini batch. So it kind of subsamples from the graph, puts that on GPU, but it doesn't need the entire graph at once. So now we want to find a way to kind of integrate fairness into these functions, into this iterative representation learning. So individual fairness specifically dictates that, similar individuals should be treated similarly. This is a fairly intuitive notion, but it is actually kind of quite complex to translate. So in a general setting, we say if we have these two data points and they were somehow similar in their input space, maybe defined by their features or somehow, then they should be similar in the output space once their representations have been learned. So the authors of the redress framework interpret this for the graph setting. So if you have two nodes and they have feature vectors and there is some distance, say the cosine similarity between these two feature vectors, then once the representation has been learned, the distance should remain somewhat bounded. So similar items, which were similar before you trained the graph-neural network, should be similar afterwards. And this lends itself very nicely to the recommender system setting because innately in recommendation systems, we are already talking about similarity. And this can be seen as a form of producer fairness, right? So for example, in the music setting, you have these two artists and they were initially similar. Once you kind of take everyone's opinion about them, they should remain similar. So now I will dive into the redress framework. I will present how it works and how we have operationalized it in our experiments. So the premise of this framework is that it is an in-processing method that combines utility loss and fairness loss in this like two-step training regime. And I'll go into more detail in a minute, but I think this visualization is very nice. So how is fairness defined in this space? So say we have a graph. We'll take this very small one here. And when you take this graph, you can define two similarity matrices. One is called SG, and it is based on the initial feature space. So information given for each node, the similarities between each of the nodes. And then there's SY hat, which is once the representations have been learned, we once again apply the distance metric and we see kind of what are the similarities between the nodes now. And so then for each node, you can generate lists. You can take one list from SG where you take, you take the top 10 most similar items using the similarity values in that matrix. And you can do the same thing for the learned representations. And so in this particular case, individual fairness holds if the two lists are consistent with each other. But as you can see here, the order is not the same. The position of these two items is not the same. So individual fairness is not holding. So now, in order to make this a differentiable functions, the authors of redress take a probabilistic approach. The similarity matrices are two matrices of size V by V, where V are all the nodes in the graph. And this is converted to a probability tensor of size V by V by V, where the UVith entry in the tensor essentially represents the probability that the node V is closer to U than the node I. And this is done for both of the similarity matrices. So for the learned representation matrix, the values are, we use a sigmoid function and the values are taken from the learned representation similarity matrix. And for the a priori, it's a simple binary cross entropy loss. And so once we have these two probabilities, we can use cross entropy to train between the two of them. And in order to have this total loss, you kind of sum over all the nodes in the graph. But if you take a look at the equation, this is not very tractable because you have to go over every node and then every node pair. And so once again, if you have a large graph, this is no longer reasonable. So what the authors of redress propose is to simplify this by using the NDCG metric as essentially a kind of mask. So this is really a clever way to do it because NDCG is already used in information retrieval as a way of comparing two lists. So there's this idea of an ideal list, and we can see that as kind of the ordering that is presented by SG, the initial input information. And then there's this predicted ranked list, which is taken from the learned representations. And what we're looking here is the delta, the change in NDCG. So you can define, concretely here, just to give a simple example, you have this ideal list, which is taken from SG, which has an ordering of the nodes. Then you have a predicted list, which is taken from SY hat. And then you look what would happen if we swapped two indices. And as you can see, you do this for only the top K values. So for example, the top 10. And so this zeroes it out. If you're not looking at the kind of nodes that are lower down in the list, you're kind of just comparing what happens if we swap the order of maybe the top 10 values for each of the lists. So going back to this training framework, we have now defined, what is the fairness loss? What is the fairness notion? How is it being operationalized here? And so in practice, you need a utility loss for the first warm-up training period. So this is just the cross-entropy loss, which is classic for link prediction. And then there's this fairness loss, which we have now just defined. And so you can kind of create this total loss for the fairness training regime, which interpolates between the utility and the fairness using a gamma constant. So you can weigh how important fairness is now. And so in practice, kind of as the visualization shows, what we do is we have 2 rounds of training. We have the warm-up period where we just use the utility loss. And we do this because you want to start with relatively good embeddings. And then you have this fairness training, which is where you fine-tune these embeddings so that the lists that are generated from them are consistent with one another and therefore individually fair. So again, just to point out, what is it that we did? So initially, the way that this framework was proposed, it was compatible with GCN, which cannot train over a large graph. So what we did is we implemented GraphSage, which is scalable. And then we implemented this redress framework into the training regime for GraphSage. And so what we're looking at is, the core subsampling of GraphSage. How does that change the way that fairness is being promoted? Is it faster? Is it better? And also, one of the key hyperparameter decisions that you make with GraphSage is what is the size of neighborhood, the P, that you will be sampling for? And so how does that affect the individual fairness? So we do this on 2 kind of real world data sets, but it's important to note that we're very limited in what we can experiment with here because GCN is not compatible with a larger graph. We tried, I swear. Now I will just kind of present our results. Before I dive into them, I'll just kind of explain how to interpret them. So we have these 2 data sets, and we have this vanilla GCN, vanilla GraphSage, and then redress GCN, redress GraphSage. So these are kind of flush with the 2 stages of our training. So the vanilla GCN is just utility-based, and the redress GCN is once we have completed 1 round of the rounds of kind of the warm-up training and also the fairness promotion. And this is the same for GraphSage. And so when you're looking at both the AUC and the fairness, higher values are better. The fairness is calculated here by taking the NDCG that I explained before and averaging over all the nodes. So essentially saying how in line are the 2 lists with each other. And what you can see here is that clearly redress GraphSage is outperforming redress GCN, both in AUC and in fairness. I mean, AUC has been proven many times before, but the fairness is actually quite interesting. But another phenomenon that was even more exciting for us is that even without fairness mitigation, there's something about GraphSage that is, promoting fairness innately. And I will come back to this in a second. Another really exciting thing is that this is done much faster. It takes many, many fewer epochs to converge to kind of good values for the representations and also kind of fair values. So going back to kind of this question of like why vanilla GraphSage is outperforming redress GCN. In order to hypothesize why this might be, we went back to how GraphSage differs from GCN. So GraphSage innately is using these like more local neighborhoods when it is promoting its fairness. And so what we were thinking is that, intuitively, the fine tuning that needs to be done to the representations may differ depending on which neighborhood you're working with. And so maybe using a smaller localized neighborhood makes it easier to figure out what is causing inconsistencies among 2 nodes that are near each other, because what causes unfairness in different groups may differ. It may not be universal for the entire graph. And so the way that we tested this is by looking at different sized neighborhoods. So as you can see, this seems to support our hypothesis because the smaller the neighborhood, the better the fairness. And so this is kind of really exciting to find because it seems like there's some sort of property here. So yeah, these are our kind of preliminary conclusions, we seem to have found some sort of relationship between having smaller neighborhoods and promoting individual fairness. And this kind of was shown empirically when we implemented GraphSage. Also exciting is that we can show that mini batch training doesn't kind of take away from the feasibility of promoting individual fairness. And this is really important because if we want to kind of operationalize individual fairness, it needs to be scalable. Another really exciting thing is that GraphSage is the younger brother, one can say, of a state-of-the-art recommender system called PinSage. And so this leads the way for implementing this individual fairness framework into a recommendation system setting. Right now it is kind of just graph neural network based, but yeah, there's room for the next steps. And so further work we want to do, right now we're using cosine similarity, right, to kind of bound as a distance metric. We also experimented with Jacquard and a few others. So this is something that we're, kind of openly exploring. Of course, extending into bipartite graphs. We don't want to just say, all the items should be similar. We should have some notion of how they're being experienced by users. And then also exploring the effects of other mini batch constructions. So, GraphSage constructs its mini batches using nodes, but there are also other methods. There are layer-based methods and graph-based methods. And so we're openly exploring these methods as well. So yeah, thank you so much for listening. I'm open to any questions, and we will be uploading the GitHub repository. There's code there, but there's no README yet. So we're on it.
My name is Daniel Schlöer from University of Würzburg, and today I will present you our use case of medical diagnostics recommendation systems. So as the title suggests, medical recommender systems, in our case, shall be employed in the hospital context. So we are working with the University Hospital in Würzburg for this. And through my talk, I will just start with a small example illustrating the use case within the hospital where we want to use the recommender system, and then come to some ethical questions, concerns, and some positions of us regarding this use case and recommender systems in this use case. So for our example, consider a patient admitted to the hospital who undergoes some initial examinations up to some point when the physician has to write down his findings and later decide what to do next. And in our case, his options are mainly limited to radiologist options regarding the next steps in the treatment. And this is also the way we frame this recommendation setting as prototype. This has some specialities. As you can see or think, the recommenders system, the use between the physician and the radiologist department involves some communications. So the requesting physician, who requests in this case the broader category of an X-ray of a leg, sends his request to the other department where it has to be processed and refined. And the other department finally has to select from a very large list of precise treatments and examinations such that the patient will get the right examination, and it can be scheduled, and of course it can also be billed. And this is the setting where we want to use a recommender system. As you might imagine, the situation where both medical assistant and physician have to talk to each other implies some communication overhead, which we want to avoid. So finally, we want to empower the physician to directly choose from the large list, or by using a recommender system in this case. This, however, comes with some ethical questions, as we are, in this case, in the medical context. And of course, the patient is the most vulnerable stakeholder in this situation, which we have to especially care about. Yeah, so in the following slides, I will discuss some ethical implications of a recommender system at this stage. But it's not only the patient who is involved in this setting, but also the medical assistant who, if you recall the slides before, was in the process, but is then replaced by a recommender system. This, of course, requires that a recommender system works well enough, but if this is the case, and we hope then finally it is the case, that it has some consequences for the assistant, which can be on one hand positive, as it may reduce the workload, but it also can be negative if the hospital decides to cut cost. It gives them the opportunity to bring their jobs at risk to some extent. Yeah, this is also in line with literature, where which says that the organizational context has to be accounted in such a situation. And yeah, just want to remark that this is also maybe a perspective which might be usually forgotten in this situation. The other perspective is the patient's perspective. The patient can save time, and this might be crucial time for his well-being, and of course this can improve the care quality overall. When it comes to fairness, the question is which sense of fairness to adopt for this situation. One could choose the procedural view, where every participant in this situation could have the same chances participating in this whole context, or an outcome-driven perspective, where, for example, marginalized groups and non-marginalized groups are compared by the outcome of the recommendation or of the final process where the recommendation is involved. The latter option might seem even more interesting, as it could reduce somehow unfairness in the status quo of the hospital context without even recommender systems employed in this situation. But it raises another question, which is how to define the outcome in this situation. And this is non-trivial question, as it is not directly measurable what impact does the recommendation of the recommender system has on the overall success or non-success of the treatment of the patient. And there's another thing which is not really positive, but it has to be accounted in a realistic way. And this is the economic reality of health system and hospitals, where the possibilities of examinations and treatments might depend on insurance level of a patient, which somehow is not desirable, but has to be accounted to make the recommender system work in reality. So to summarize, there are trade-offs which have to be taken, but they should be always evaluated for their clinical and also for their ethical validity. Regarding transparency, the view is somehow twofold. So one literature work finds that physicians have to account for their decisions and therefore will reject non-transparent AI systems in general. Another work by Clement et al. Says that transparency may favor acceptance of low quality recommendations, which is not desirable in our case. And so there's some tension between those two positions. And we have, for our design, to think about which one to adopt. And especially since for accountability and compliance reasons, we rather see this recommendation as supportive tool to improve the selection and not the decision. Yeah, we stay with the second perspective and think that automatic rationalization might shorten the thought process and thus be not beneficial in this case. Now I come to the most important aspect and also the last aspect which I want to talk about. It's the safety. Safety can be approached from different angles. System-centric perspective is I guess most common perspective, where we have a look at the performance of the recommender system. This could involve offline evaluation before employing such a system in a real-world setting, but also raises the question how to evaluate such a system, especially if you think about the data, which is not curated at all and may also contain wrong data or noise, which with maybe severe influences on the health of a patient. So regarding safety, we have to adapt a holistic view. Of course, the performance is important, and the performance has to be in a range where the beneficial somehow outweighs the risks. But safety and also all other ethical aspects have to be constantly monitored during operation to be sure that the patient isn't harmed in any way. By this, I want to conclude my talk. Again, sorry for the technical difficulties at the beginning. And yeah, maybe we can discuss later some ideas, questions, or suggestions. Thanks.
Okay, so like many other machine learning system, recommendation system can be vulnerable to malicious attacks. And designing a robust and unbiased recommendation system is required for fairness and stability. For example, attack can cause wrong or biased prediction, which can lower the accuracy of the recommendation system. Also, it can infer about users and items that customer purchase. Also, it can compromise the fairness of the entire system. So the proposed recommendation can be derailed by the attacker. So attacker can possibly manipulate the popularity of the desired target and product and group, and it can infer the personal information on the recommendation result. So I think mainly this workshop is focused on fairness. However, fairness can be closely related to also accuracy, utility, as well as the security. So I'd like to introduce a couple of attacks, popular attacks against the recommendation system. So the first one is a shilling attack, and second attacks are adversarial attacks, which can lower the accuracy and produce the incorrect result. So shilling attack is based on statistical analysis. Yeah. So statistically designing the attack so that it can change the rating of the individual item or popular item. So random attack and average attack and bandwagon attack and segmentation attacks are there. So random attack is to change random rating of all items, and average attack is average rating of individual item, and the bandwagon attack is to manipulate the weighted rating of popular items, and segmentation attack is weighted rating for some targeted group. So basically the idea is injecting this fake profile into the this matrix so that you can change the rating in this way. So this is known to be one of the popular attack methods against recommendation system. Also, adversarial attacks are also possible. So many computer vision system or natural language system, NLP systems are also known to be vulnerable to this adversarial attack. So adversarial attack is basically adding some perturbation or noise to the input center, and then you can change the output result. So this can be also applicable to recommendation systems where attacker can precisely add the perturbation and noise into user rating matrix or user item or user or item additional information matrix, so that our recommendation system model can produce incorrect results, so that it can promote and demote the certain items and in the intention for the attacker's need. So these types of attacks can compromise the fairness of the recommendation systems, and they recommendation can vulnerable and produce biased recommendation results. So one possible defense would be adversarial training, like adversarial defense for the computer vision system. Recommendation can include those adversarial noise examples and then retrain, so that it can be more robust against those types of adversarial attacks. That's one possibility. Another method or something based on knowledge distribution, where transferring knowledge from larger model to small model, and the student model can be more robust against these types of adversarial attack, and doesn't require retraining entire data set, so it can be more efficient. And also we can try to detect some fake input at front generated by the attacker, but it can possibly have some low generalizability of the algorithm. And also there can be other challenges. Certainly recommendation system can be exploited and can be attacked. But in many literature, most attacks assume white box model, which is we know the details about recommendation system details, like their neural network structures, so that attacker can optimize attack, etc. However, this cannot be realistic in some way. So more realistic attack, such as black box attack, are more need to be researched more. And also for accurate modeling, we need a good attack data set, and then labels are required. However, it is not easy to acquire those. And also we need a more efficient defense method that do not require retraining. And it is in real world, it is not easy to retrain an entire recommended system frequently. And also attack detection, we can look at as an anomaly detection problem, where we have a attack and normal data. So we try to detect the attack from the anomaly detection perspective. However, there are many challenges in this area, unbalanced data set and labels, and etc. So we may consider defense from anomaly detection perspective. Also, previous speaker said good representation is needed, and biased representation are not good for the recommendation system. So certain recommendation system network are more vulnerable to certain types of attacks. So for example, GNN can be more vulnerable in certain types of attack schedule, right? Concluding, recommendation are exposed to a variety of attacks, and this discussion paper is to investigate attack and defense from the fairness perspective. And future work is really required to study the effect of adversarial or various types of attacks on fairness of the recommendation system, and then coming up with a better and more effective defense methods are required to maintain the fairness and privacy of the user and the entire system. So yeah, this concludes my talk. And if you have any questions, you can email me. Okay, thank you.
Last presentation of the conference. I promise I will try my best to make this worth your time. So I'm Jessie Smith. I'm from the University of Colorado Boulder, and this is work that I did with Lex Beatty from Spotify, who's sitting in the back right there. And this is RecSys fairness metrics, many to use, but which one to choose? So there are many ways that we can measure and evaluate fairness in our recommender systems, as we've learned in previous years and as we've discussed thoroughly today. In other words, there's many metrics for us to use. But unfortunately, the reality is that machine learning practitioners and industry are really lacking the guidance that they need to know which evaluation and which fairness metrics to choose that appropriately match their fairness context. In other words, they don't know which fairness metric to choose. So we've identified some challenges, some practical challenges that practitioners face through some interviews and also some literature review. And we've refined this to two main tenets, I guess. These are challenges with scoping the fairness problem and challenges with the complexity of fairness metrics in general. I'll go over a bit of this at a high level. So when we want to begin measuring fairness and evaluating fairness in general, the first step is to think about what it actually means for our recommender system to treat users fairly, and also what it means for our recommender system to treat them unfairly. We have to come up with a fairness definition. And this is no easy task because fairness is this subjective, theoretical, qualitative construct, but we're attempting to quantify it and measure it empirically. So fortunately, we can look to disciplines like the social sciences, and we have a framework which is called measurement theory that allows us to capture these complex theoretical qualitative constructs and at least attempt to empirically quantify them. But as I said before, this is no easy task because there are a lot of challenges to do this. And one of the most important challenges, I think, on the screen is number one, which is determining if there even is a way to quantify the type of fairness that we are attempting to measure. And that's not always the case. Beyond construct validity, there's also some more practical challenges that practitioners face. So previous research has done interviews with machine learning practitioners, and it's discovered that a lot of practitioners worry that they might just choose the wrong fairness problem in general. They might choose the wrong user base, or they might incorporate their own biases into their fairness evaluation, which honestly is inevitable. And then beyond this, when we go outside of academia and into practical industry context, we also have to align our fairness goals with the goals and the principles and the values of the organization and the company that's hosting the recommendation platform, because we have to make a business case for AI ethics often. So beyond the practical, more, I guess, institutional constraints that practitioners face when trying to evaluate fairness in their systems, there's also the challenge of actually deciding on one or maybe several metrics to choose before we even get to implementation in the first place. So as I said before, a good starting point is to think about what our fairness definition is. And as previous research has discovered, there are dozens of ways that we can define what fairness or unfairness means. And this is drawing from other disciplines like moral philosophy or political science or the humanities. And I think I even learned about a few more in presentations today. So there's a lot of options. This summer, we conducted a literature review of 42 different recommendation and ranking papers on fairness. And we discovered that there were more than 34 fairness metrics that we could choose from for any given fairness problem. And this excluded quite a few metrics that I'm sure we missed, some new metrics that were introduced today, and also metrics that were not as relevant for practical purposes, like maybe they assumed that we had access to ground truth labels, for example. And of these 34 metrics, quite a few of them allow us to actually evaluate fairness for multiple definitions for one given metric. So this means that if we have probably way more than 34 metrics, probably way more than just a dozen different fairness definitions. And all of these metrics can be modified based off of our value of hyperparameters or fairness thresholds. We're now looking at this complex decision-making space where there's possibly hundreds of ways for us to evaluate fairness for one given context that might all be equally appropriate. Pretty challenging. And beyond just what we are measuring, we also have to think about who we are measuring fairness for. So as previous presenters said, there's different kinds of stakeholders in recommender systems. And we discovered just in our small literature review that 21 metrics that we found were geared towards providers or producers, while 13 were geared towards consumers. And sometimes fairness goals for different stakeholders might come into conflict with one another. So we have to choose which stakeholder wins that battle. And once we do select a stakeholder group, now we have to choose between measuring individual fairness or group fairness, whether we want to treat similar individual users similarly or similar groups of users similarly. And once we decide if we want individual or group fairness, now we have to figure out which part of our complex recommendation pipeline we actually want to measure fairness for. Do we want to measure fairness in our top K rankings, in our candidate pool generation, in the global distribution of recommendations on our entire platform? All of these could be equally appropriate candidates for our fairness problem. And finally, sort of the crux of the problem, we have to choose an appropriate proxy for fairness in our data with the data that we have available. So which features are we actually looking at as potential alternatives or proxies for what we mean by fairness? Do we want to try to maximize equal accuracy rates, equal loss rates, equal item exposure, equal click rates? All of these could also be equally appropriate. So in summary, when this is a very complex decision-making space, we begin with this idea of this theoretical high-level construct of fairness and wanting to do good in the world. And we have to go through many complex decision-making steps with individuals and groups of people who often haven't even been trained in any sort of fairness or ethics work. And this is all before any kind of implementation can be done. This is just to choose possibly one single metric to evaluate our system. And I guess my biggest takeaway from this work so far is that I think of fairness work, at least I like to think that the motivation behind what a lot of us do, and the reason why we do this kind of work is because we want to make a positive impact in the world. And people are doing really amazing work in this room and in this community. And if we don't help practitioners utilize that work, then we don't really have a lot of potential to make that positive impact that we want to make. So sort of a call to action, I guess, to close. And if you want to learn more about this work, read the very short paper and the hopefully in the future longer paper at some point. And that's all for now. Thank you.